In this learning path, we will be taking a look at how we can build decentralized applications for the Ethereum network. To get the most out of the courses in this path, there are a few prerequisites in terms of theoretical knowledge as well as practical skills. First of all, you need to have some fundamental understanding of blockchain technology. Though you don't need to recall all of the specific details of the Ethereum proof of work algorithm, for example, you will need to understand exactly what makes up a blockchain network, and will need to have an understanding of what smart contracts are, what Ethereum account addresses represent, and other high-level knowledge of how blockchain technology works. In addition, since this course involves the development of both smart contracts as well as front-end applications in order to construct a decentralized app, it will greatly help if you have some prior coding experience. Some familiarity with web development and JavaScript will be especially useful. Also, if you have some prior experience using both the Solidity language for smart contracts and the Truffle framework in order to simplify the processes around building, testing, and deploying smart contracts to an Ethereum network, then following the labs in this course will be made a lot easier for you. So with the prerequisites covered, let us dive right into building decentralized applications. To start off, we will look at an example of a group of entities who would like to record all of their transactions on a blockchain. So if you take in a retail supply chain, you can consider that this involves a factory which manufactures some goods, and these goods will eventually make their way to a retail outlet where customers can purchase those goods. Typically, such products won't get to the retailer directly, but will in fact be sold off to a distributor by the factory. This distributor, in turn, will hand over the goods to a wholesaler, and from the wholesaler, the product will be sold off to a retailer who will then display the goods on their shelves. So in this particular case, you can say that there are three different transactions involved. The sale of goods from the factory to the distributor, then from the distributor to the wholesaler, and then finally from the wholesaler to the retailer. Traditionally, in such a case, each of the participants will maintain their own ledger in order to record the transactions. Each of them may have their own implementations of a ledger. Some of them may still be recording all of their transactions in books. Others may be using Excel spreadsheets, and there may be those who make use of relational databases. Whatever the ledger implementation though, it has been found that these ledgers are often inconsistent. This could simply be down to how exactly each of these entities records their transactions, or it could also be genuine mistakes on the one doing the data entry. However, the problem with such an approach is when there is a dispute with regards to the details of a specific transaction. Since each of the entities will have separate ledgers and different standards for recording information, these ledgers cannot really be relied upon in order to settle disputes. This can lead to an erosion of trust among the participants, and this does pose a problem when it comes to doing business. This is because doing business is a lot easier when all of the parties involved can agree on the specific details of the transactions they have been involved in. So the solution for the participants in our retail supply chain is for them to adopt a common standard for recording transactions, and to also ensure that all of the transaction details are written to a common ledger. And we can now assume, for the sake of our example, that it is the retailer in the supply chain who takes the lead in setting up such a common ledger. So this shared ledger can be implemented as a relational database, for example, and all of the entities involved, starting from the factory, the distributor, the wholesaler, and the retailers themselves, will be given access to this common ledger. And they'll all have an application, let's just say some kind of web app, in order to record the transactions on this common ledger. So in this particular case, this database represents a centralized ledger, but this can also be a decentralized one, where each of these entities in the supply chain maintains a copy of this ledger. And how exactly will the transactions be recorded? As touched upon, we can have a web application which will be developed by the retailer, and this will have a simple user interface which can be used to enter all of the transaction data. This application will be connected to a relational database at the back end, and it will ensure that all of the transaction data which has been entered from the UI will be recorded on this database. So now, all of the entities involved have access to the exact same data, and they have also agreed upon a common standard in order to write the details of the transactions. If there are any disputes with regards to the details of a transaction, all these parties only need to consult this shared database, and the details will be right there. Problem solved, right? Well, not quite. This is because in this particular solution, which we have taken a look at, all the parties need to place their trust in the retailer. Now, all of this is fine as long as the interests of the participating entities are perfectly aligned. However, this is not something which can be relied upon for a long period of time. And it is possible that at some point, a retailer could become fraudulent or at least become negligent when it comes to maintaining this shared solution. Another problem with this particular approach is that this requires a retailer or at least one of the participating entities to take the lead and build this solution. In reality, though, most of the entities in a supply chain would like to focus on their own immediate business interests rather than worry about setting up an IT solution. This is because setting up an application, as we have discussed, involves a lot of work. First of all, one will need to build and maintain infrastructure for this. This could either be by means of having their own data center or setting up resources on the cloud. And very importantly, they will also need to handle the security for their application and prevent malicious entities from accessing the transaction data. Now, the question is, what happens when someone does manage to evade all of the security measures and is able to tamper with the data which is recorded on the shared ledger? In the case of a relational database, there is no systematic way to detect the fact that the data has been tampered with. This is especially a problem if the one doing the tampering happens to be a database administrator or someone with a high level of access in the system. This means that this shared solution we have discussed is effectively a single point of failure. Even if it is implemented as a distributed ledger, someone with a high level of access and knowledge of the network could go ahead and make changes to each of the copies of the ledger and still go undetected. The bottom line here is that the users of such a system cannot always trust the data which they see, which means that we are effectively back to square one in terms of the problem which we defined at the beginning of this video. It is not easy to do business when all of the entities involved cannot agree on the details of their past transactions. So, this particular solution involved a web application and a relational database at the backend in order to record the transactions. And the question now is there a better solution for all of these entities in the retail supply chain? And the answer is yes. So we can retain a web front end. However, at the back end, we can replace the relational database with a blockchain. A blockchain is a secure place in which to record transaction data because there are mechanisms to ensure that the data cannot be tampered with without being detected. In the previous video, we covered the fact that for the participants in a retail supply chain, it made sense for them to record all of their transaction data on a blockchain. I had alluded to the fact that blockchains offer a secure and tamper-proof structure in which to record such information, and in this video we will take a closer look at exactly how that is achieved. So for the participants in the retail supply chain, we discussed that they can enter the data of the transaction through some web application, and this will enter the records for the transactions on a blockchain. We had discussed that recording the data on a blockchain was an improvement over storing that in a database, and this is because in a relational database, there is no systematic way to detect any tampering of data. So what exactly is a blockchain? One definition is that it is a list of records where the records are stored across a sequence of blocks, and these blocks in turn are chained together using cryptography. We can visualize exactly what this means. Consider that we have 9 different records which have been split across 3 blocks. So here this is block number 1, which includes records 0 through 2. This has been chained to block number 2, which contains a further 3 records, and this in turn is chained to block number 3. You will notice that there is an ordering of the records within each of the blocks, and in fact there is an ordering of the blocks as well due to this chain structure. And how exactly is this chaining accomplished in a blockchain? Well, this is where the concept of a cryptographic link comes into the picture. And we will soon see that it is this use of cryptography which prevents the tampering of data on a blockchain. Another important thing to keep in mind is that this blockchain is going to be distributed across multiple nodes in a blockchain network. In the case of our retail supply chain example, you can consider that each of the 4 participants will have their own copy of this blockchain. So in essence, a blockchain happens to be a distributed ledger of records. Now, if one of these copies of the distributed ledger were to be tampered with, we will now see that there is a systematic way to detect this tampering, and this detection is possible thanks to the inclusion of the cryptographic link in each block of the blockchain. So within each block, there is a cryptographic hash of the previous block in the blockchain, and each block will also contain some additional information. This could, for example, include a timestamp for when the block was added to the blockchain. There will, of course, be all of the transaction data or any corresponding records which need to be stored on the blockchain in a secure manner. There can also be some additional metadata, and this could represent some information about the transactions themselves. There can also be other information included within the block, and this can vary according to the specific blockchain implementation. So why exactly does this inclusion of the cryptographic link prevent blockchains from being tampered with? Well, consider that we have these 3 blocks in a blockchain, and each one you will see has a hash of the previous block in the chain. This, of course, does not apply to the genesis block or the first block in the chain because there is no previous block to consider. You can also keep in mind that each of the entities in the blockchain network, in our example, each member in the retail supply chain, will have their own copy of this blockchain. So, consider that some malicious entity tries to alter the details of one or more of the transactions in the genesis block. This will mean that the hash of this first block will be different, and the nature of cryptographic hashing means that this first block hash can be vastly different for even a minor change in the transactions. Now, this alteration has been performed on just one of the copies of the blockchain, and even with this copy alone, you can instantly see that the blockchain is not consistent. This is because this modified hash in the first block is not the same as the first block hash which is included in block number 2. So for this particular blockchain copy to be consistent, then the block of the first hash included in block number 2 will need to be modified. But you will observe that this in turn has the effect of changing the hash of block number 2, which in turn will change the hash of block number 3, and this will go on right up to the latest block in the blockchain. Now, for any of the other nodes in the network to detect that this particular blockchain copy has been tampered with, all they need to do is to check for the hashes of the latest blocks in the blockchain, and they will recognize that there is some mismatch in the copies. If there is one particular blockchain copy which has the mismatch, then they can go through the hashes of each of the blocks to figure out where exactly the mismatch has originated. One question you might ask at this point is, what if this malicious entity tries to change the transactions in such a manner that the block hash does not really change? Since multiple inputs can produce the same hash output, this is something which is theoretically possible. However, the very nature of cryptographic hashing means that these hashes cannot really be reverse engineered. And it is almost impossible for someone to reproduce the same hash output without significantly modifying the transaction input details to the point where the data makes absolutely no sense. So the bottom line in all of this is that any attempt to modify a previous record in a blockchain will easily be detected by the system. So just to summarize, if a blockchain is used instead of, say, a relational database in order to record your transaction data, then any of the transactions which have been written cannot really be altered after the fact. Well, theoretically, it can be by altering all of the subsequent blocks in the blockchain, but as we have observed, this is very complicated and requires consensus among multiple nodes in the blockchain network. Also, hash output cannot really be reverse engineered, so it is nearly impossible to make alterations to the transaction data without being detected. Also, this cryptographic link in the blockchain ensures that every single record on that blockchain is both verifiable and tamper-proof. So when using a blockchain, you can rest assured that the data which you see on that blockchain is exactly as it was entered in the first place. So now going back to the problem which we were trying to solve for this retail supply chain, we were trying to create a system where all of the parties involved can agree on the details of the transactions, and for this, we needed to make use of a structure where everyone can trust the data which is recorded on it. And this is exactly where blockchains come into the picture. So now that we know that blockchains are a secure place in which to record transactions, what is the exact mechanism involved in order to write these transactions to the blockchain? Transactions is quite a generic term, and the nature of transactions and the specific details which need to be stored for it will vary depending on the use case. What we really need is a means for us to be able to define our own transactions, which includes not only the actual data which needs to be recorded for the transactions, but also some processing logic. And this is exactly where smart contracts enter the picture. One definition of a smart contract is that it is a protocol to digitally specify, verify, and potentially even enforce the terms of a contract. Taking a look at some of its properties, we can think of a smart contract as being very similar to a traditional contract, except that in this case, the contractual terms are specified in terms of code rather than in legal terms. One feature which distinguishes code and smart contracts from traditional contracts is that there are no legal gray areas in this case. That is, contracts are strictly non-ambiguous and you know exactly what they do by just reading the code. Another feature of smart contracts is that they are both immutable and distributed across multiple nodes in a blockchain network. So there is no single party which controls a smart contract. And one very crucial feature of smart contracts is that they often serve to minimize the involvement of trusted third parties in many interactions. So going back to our web application which records transaction data on a blockchain, what will actually be happening is that this application will be invoking methods defined within our smart contracts to record these transactions. In the previous videos, we have covered the fact that it makes sense for many businesses to record their transactions on a blockchain. We will now take a look at the notion of a decentralized application and what exactly it means in the context of the Ethereum network. So we have previously seen that there are several benefits to recording transaction data on a blockchain. First of all, blockchains are distributed across multiple nodes in a network, due to which there is no single entity which is in control of the blockchain. The transaction data written to a blockchain is both immutable and can be verified, and with the use of smart contracts, it is possible to minimize or even entirely do away with the involvement of trusted third parties in many different interactions. So once an organization has decided to use blockchains in order to record their data, they may ask the question, what exactly are the types of blockchain networks which are available? Once an organization decides that they wish to be entirely transparent with all of their transactions, they will opt for one of the public blockchain networks. And out of these, the most well-known are the Bitcoin network, and then there is the Ethereum network. So what exactly is meant by the term public blockchain network? Well, this means that anybody is free to join the network, and you don't need to receive an invitation or go through some vetting process in order to become a member. As a consequence, public blockchain networks typically have many nodes. In fact, the Bitcoin and Ethereum network have several thousands of nodes. The public nature of such networks also means that the details of the transactions and also some of the smart contracts will be available for all to view. Even though personal information may be obscured behind account addresses, if you happen to transact with someone, they will have access to your account address, and they can use that address in order to view all of your transaction history on that blockchain network. So this transparency is something to keep in mind when using public networks. Another important factor with these networks is that given there are several thousands of nodes, and many of them cannot really be relied upon to behave in a correct manner all the time, there is usually a complex consensus mechanism for all of the participating nodes to come to an agreement with regards to the correct state of the blockchain. In the case of both Bitcoin and Ethereum at the time of this recording, the proof of work algorithm is in use. So, let us take a closer look at each of the public blockchain networks we have discussed, starting with Bitcoin. One issue with this network is that it supports just one specific kind of transaction, which is the transfer of the cryptocurrency Bitcoin from one account to another. There is no scope in which you can define your own transaction because Bitcoin does not support the concept of smart contracts. So when we take a look at the Ethereum network, this happens to be the most mature of the public blockchain networks available in the market, and it also happens to be the most widely used. A big reason for this is that Ethereum supports the concept of smart contracts, so it is possible for you to define your own bespoke transactions. Another thing to keep in mind is that Ethereum has its own cryptocurrency, which is known as Ether, and there is a fee associated with any transaction which you invoke on the network, and this transaction fee needs to be paid using this Ether cryptocurrency. So if you'd like to record your transaction data on a public blockchain network which is mature, widely used, and secure, then Ethereum is a network which you should strongly consider. And in order to record your transactions on the Ethereum blockchain, what you will likely need to build is a decentralized application. So what exactly is meant by this term decentralized application? Well, a very simple explanation is that this is an application which runs on a network of computers rather than on a single host. And given that decentralized application is quite a mouthful, it is often shortened to the term dApp. Now, moving along to the term dApp in the context of Ethereum, you can consider that such a decentralized application will have three different components. The first of these, which will be most visible to the users of the application, will be a web UI, and this UI in turn will connect to a smart contract which has been deployed to the Ethereum network. As we have discussed, it is within the smart contract where you can define exactly what the transactions which you wish to record on the blockchain will look like, and all of the data and logic of the transactions can be coded right here. This, in a nutshell, is what a decentralized application is in the world of Ethereum. A user can enter details for a transaction through a web UI and then call one of the transactions defined within a smart contract through this UI. The contract, in turn, will implement some kind of transaction logic and then write down the data for the transactions in the blockchain. And since any mechanism to record transactions on the blockchain is a decentralized process, this is in fact a decentralized application. So out of these three components, what exactly does a developer of a decentralized application need to work on? Well, two of these three are in the direct control of the developer. The first of these, of course, are the smart contracts where you implement the transaction logic. And then also the web UI which connects to the smart contract will need to be built by the developer. One thing to keep in mind is that both of these can be developed separately, and depending on the organization, the contract and UI development may be performed by entirely different teams. So let us take a look now at what exactly is involved in the development of smart contracts. A developer will start off by building and then compiling the smart contract, and then following that, they will need to deploy the contract to an Ethereum network. They will then perform some tests on this contract, and for doing that, they will be invoking the various contract functions and then playing out different use cases for that contract. And during this process, they are likely to find some bugs or definitely identify areas for improvement, in which case they will essentially repeat this entire process of development, compilation, deployment, and testing. And the cycle will repeat until the quality of the smart contract is considered good enough for production deployment. Moving now to the process and the goals of developing the user interface. And one of the goals for the UI developer will be to make this interface interactive. They will also need to establish a connection between the UI and a deployed smart contract. And once that has been accomplished, they will then test out their UI by invoking queries and transactions defined within that contract from the user interface. So when building a decentralized application for Ethereum, there are many steps involved and many things to wire up. And in order to simplify all of these tasks, there is a Truffle Suite of tools. The first of the tools in this suite is known as Truffle or the Truffle Framework, and this is meant to add structure and to automate the processes around building, testing, and deploying smart contracts. Then there is another tool called Ganache, which is used to provision a private Ethereum network to which to deploy your smart contract and run quick tests during the development and maybe even the testing phase. And then finally, to help with the UI development, the Truffle Suite also includes Drizzle, which are a collection of JavaScript libraries which perform a lot of the wiring to connect your UI over to a deployed smart contract. In the previous video, we discussed the fact that building a decentralized application involves essentially two separate phases: developing smart contracts and then developing the UI. Now we will take a look at the Truffle Suite, which includes a collection of tools to help with the development of each of them. We cover the fact that developing a smart contract for your decentralized application will start off with the development and building of the contract, then deploying it to an Ethereum network. And in the case of the development phase, this is usually to a private network. We will then execute some tests on our smart contracts, and we'll go ahead and repeat this entire cycle until the contract is of high enough quality. So one thing to keep in mind is that there are several steps involved in smart contract development, and there are different ways in which this development process can be sped up. For example, if there is some predefined structure for every contract project, it will be much easier for developers to jump from one project to another. It'll also mean that developers will know exactly where to look for each of the files which make up their contract project. Another crucial factor is some simple and systematic way to integrate your smart contract project with Ethereum networks. This could either be to a private network or even to one of the Ethereum test networks or even the main network. Another way to speed up the development process is to include automated testing for the different parts of your contract. And it'll also help if you have some way in which to script the deployment of your contracts to the different networks. And one feature which will be especially helpful in the development phase is a way to set up and also integrate your contracts with a private Ethereum network. Such a private network can serve as a sandbox environment in which you can test out your smart contract and then carry out some wild experiments which you may be hesitant to try out even in an Ethereum test network. Moving on now to some tools which may be helpful during the UI development phase. If there are libraries which automatically set up all the wiring required to connect the UI to the smart contracts, it will greatly help this development process. Another factor which will be useful is some way to be able to subscribe to the state of the contract so that any updates which are made to the contract will be visible in the UI. And very importantly, we will also need interfaces which will allow us to invoke the various contract functions, whether these are query operations or transactions. And all of these features which are required for both the contract and UI development are available in the Truffle Suite, which happens to be the most popular development framework for Ethereum. So at a high level, what are the features offered in the Truffle Suite? Well, for contract development, there is a way in which to enforce a standard file and directory structure, which will definitely simplify the process of deploying and testing out contracts. The suite also includes tools which integrate with the Moca and Chai testing libraries in order to perform automated testing of your contract. There are also ways in which you can connect your contract project to the Ethereum main or even the test networks and deploy the contracts directly to them. You can also make use of the Ganache tool in order to provision private Ethereum networks, which are very useful during the development phase. And you can also make use of the Drizzle JavaScript libraries in order to integrate your UI with deployed smart contracts. We can now zoom in a little bit on each of the tools which make up the Truffle suite, starting with the Truffle Framework, which is often referred to just as Truffle. This is a tool for smart contract lifecycle management, which means that this automates processes around building, testing, and deploying of smart contracts. It also includes integrations with the Mocha and Chai testing frameworks so that you can write test cases, group them into test suites, and also make use of assertions in order to test out your contract. And it is also possible for you to write down your own scripts in order to deploy your contracts to an Ethereum network. Moving now to Ganache, which is the tool you will use in order to provision a private Ethereum network. Networks set up with Ganache are highly configurable, and even details such as mining frequency and logging can be controlled with this tool. Ganache also includes an intuitive UI which allows you to view various parts of your blockchain network. There is a block and transaction explorer, and there is also a way for you to view logs, the state of your contracts, and also events which have been emitted by your deployed contracts. So Ganache is very useful in debugging your contracts and can play a big role during the development phase of your contract. Moving now to Drizzle, and these are a collection of JavaScript libraries which are meant for the user interface of your decentralized application. These libraries include a number of different interfaces which can be integrated with React components in your web application in order to invoke functions in your deployed smart contract. Drizzle also includes access to a Web3 object, which you can use to access contract data and also general information related to the blockchain network. So to summarize, a decentralized application in the context of Ethereum includes a web UI, which connects to a smart contract deployed to the network, and this contract in turn includes definitions for functions and transactions, which will be recorded on the blockchain. And out of these three components, the ones which are in control of a dApp developer are the smart contracts and the UI. And in order to help with the development of these components, you can make use of the Truffle Suite. And to summarize the steps involved in dApp development, you will first build out smart contracts and also scripts for testing and deployment of those contracts. You can then make use of the Truffle Framework in order to build the contracts, run your automated tests, and also execute your deployment scripts. And the initial deployments and testing can be done on a private Ethereum network set up with Ganache. Moving now to the development of the user interface for your application, you will need to link the build artifacts generated by the Truffle framework for your contracts with the user interface. This is so that the UI will know exactly where the contract has been deployed and will also have access to the interfaces required in order to invoke the contract functions. And then finally, in order to complete the wiring of linking your web app with the deployed smart contract, you will make use of the Drizzle libraries. In the labs of this learning path, we will be executing each of these steps in order to build out our dApp. We will now explore the concept of tokens in the world of Ethereum. These are often used in many decentralized applications, and it is something which is definitely good for you to know in case you wish to implement one for your own dApp. We can start off by defining exactly what a token is in general. You can consider that this is a bespoke currency, and like any regular currency, can be exchanged for goods and services. However, this is only in the specific domain of the token issuer. For an example, you can consider tokens which are issued often by theme parks in various parts of the world. To get an idea of how they work, consider that theme parks offer several goods and services within their own park grounds, which is their specific domains. These goods and services can include the various rides which are included within the park, and also arcade games. And there are also several stands which will be selling snacks and meals to the park visitors. Now, many of these parks which issue tokens will allow these goods and services to be purchased by means of tokens rather than with regular currencies. In fact, it may be mandatory for you to purchase these goods and services using just tokens. The tokens themselves can be purchased either at the park entrance or maybe even online with regular currencies. So each of these tokens will translate to a certain amount in euros or US dollars or whatever your local currency is. And once again, I will emphasize that these tokens are typically only used within the park grounds and cannot be exchanged for goods and services outside of them. Now, a question you might pose is, why would these parks use tokens and not regular currencies? Wouldn't it be more of a headache to manage these tokens? Well, the answer is yes. It would indeed be easier for the parks to just accept the regular currencies, but it has been proven that in many cases, such tokens have the effect of getting customers to visit the park again. One of the reasons for this is that they will likely have many unspent tokens from their previous visits, and they may find it quite wasteful to have these tokens just lie around and not be put to use. Additionally, many tokens can be set to expire after a certain amount of time, in which case they will effectively be junk. A consequence is that these customers are incentivized to spend these tokens, for which they will visit the park again and can potentially become regular customers. Also, the theme park might choose to issue rewards to regular customers in the form of tokens, which again serves the purpose of building loyalty and will encourage the customers to visit again and spend more money at the parks. In a nutshell, implementing such a token system can translate to more business. So now that we have an idea of how tokens can be put to use in theme parks, how does this translate to the world of Ethereum dApps? Well, a decentralized application may be one which offers some goods and services. Now, such a dApp can be coded to accept payment not in the form of US dollars or euros, but in the form of bespoke tokens. The creators of this dApp will first need to issue these tokens in exchange for Ether, and because these tokens are customized, it is possible for them to regulate the supply of the tokens and also define their own terms and conditions. For example, set an expiration date for the tokens. So now that we know that it is possible to code a decentralized application to accept customized tokens as payment, how exactly can we create such tokens? Well, these bespoke tokens can be implemented by means of an Ethereum smart contract. And once you have defined such a token, it is possible for any decentralized application to accept this customized token as forms of payment as long as it is coded to do so. Now, given that these tokens are highly customizable, you may just want to go out and define such a token and then include all kinds of features within it. Now, before you go ahead and explore the infinite possibilities with your token, you might be wondering, is there a template which you can build upon for your token? Are there any rules for token definitions which you can use as a starting point? And the answer to that question is yes. And this is where ERC standards come into the picture. We can now take a look at some of the properties of ERC token standards. So ERC is short for Ethereum Request for Comments. Now it is possible for anybody to create such an ERC standard, and it is up to them to publish the detailed documentation for that standard. Given the unregulated nature of ERC, you can imagine that there are some standards which are much more widely adopted than others. And another thing to keep in mind is that there is no compulsion for any decentralized application to only use ERC compliant tokens. ERC standards are merely guidelines and not strict rules. Among the widely used ERC token standards, there are usually definitions for the interfaces which your token must implement in order to make it easier to work with those tokens. For example, these interfaces can include operations in order to sell your token to someone else. The purpose of these standards is to give some structure to token definitions and to ensure that they provide some minimum functionality which makes it possible for applications to work with those tokens. When at least a minimum set of features are included, it makes it easier for different applications to adopt the use of tokens, and it is also simpler for them to switch from one token to another if required. Again, I emphasize the fact that as of this recording, there is no enforcement mechanism that a token must comply with the ERC standards. So you can still define your tokens in any way you like. Some examples of ERC token standards include the ERC20 standards for tokens which are fungible. That is, it should be possible for decentralized applications to switch from using one ERC20 token to another. There is also an ERC721 standard, and this is meant for non-fungible tokens, which may represent, for example, a house. There is also an ERC1337 standard for tokens which can be used to pay for recurring subscriptions. We can now take a closer look at the most widely used standard, which is the ERC20. This stipulates that your token definition should include operations which allow users to spend tokens. That is, it should be possible to transfer your tokens to someone else. Your token definition should also include ways in which you can authorize spends. That is, it is possible for you to assign someone else to spend your tokens on your behalf. And the token definition should also include an interface to get the data for the total supply of tokens which are in circulation. And though the token supply need not be fixed, it should be possible to get the details for the total allocation of these tokens. That is, it should be possible to determine the number of tokens which are owned by a specific Ethereum account address. These, at a high level, are the features which must be implemented for a token to comply with the ERC20 standard. Now, getting down to the lower level in terms of the smart contract for the token, what does this translate to? Well, this includes a set of functions which needs to be implemented within the contract, also a collection of events which must be defined, and your contract definition may also include a name and a symbol for your token. For an equivalent in regular currencies for the name and symbol, you can think of US dollar and USD. So what are the functions which your token definition must include to be compliant with ERC20? Well, there is a function called total supply, and this is one which returns the total quantity of tokens which are in circulation. This function has no parameters and returns an unsigned integer value. There is also a balance of function, and this accepts the address of an Ethereum account as its argument, and it will return the total balance of tokens which belong to that account. There is also a transfer function, and this is invoked by the owner of tokens in order to transfer some tokens over to a recipient, and that recipient's Ethereum account address is the argument to this function. Now, the balance of and transfer functions should be somewhat familiar since they are related to the direct ownership of tokens. There are another set of functions, however, which the ERC standard defines, and this is with regards to delegating one's own tokens to someone else. One of the functions here is called the approve function, and this is where the owner of a particular set of tokens can authorize somebody else to spend tokens on their behalf. Now, if you wish to find out how many tokens someone is authorized to spend on behalf of someone else, you can call the allowance function, and this takes in two arguments: the address of the token's owner and the address of the delegate who has been authorized to spend tokens. And this will return a value which corresponds to how many of the token owner's tokens the delegate is allowed to spend. The reason for implementing such a delegate system for the spending of tokens is to convey the fact that a company may own some tokens and may allocate some of those tokens to their employees. Those tokens still belong to the company, but the employees are free to spend them. And in order for delegates to spend the owner's tokens, they can invoke the transfer from function. This is where the delegate will specify the recipient of the tokens, and the token will transfer from its current owner over to the account of the recipient. The tokens will never hit the account of the delegates themselves. One thing to keep in mind is that for your token to be ERC20 compliant, it is only necessary for you to include these functions within your contract. The specific implementations of these functions is entirely up to you. Moving along now from the functions which need to be included in your token definition to the events which must be defined. One of the events which you must have is called transfer, and this is an event which is emitted when either the transfer or the transfer from functions are invoked. The second event which your contract must define is called approval, and this is something which is emitted when the approve function has been called. So with the inclusion of these events and the functions which we have discussed, your token will be compliant with the ERC20 token standard. In this exercise, you will start off by defining a decentralized application or DApp. You will give both the general definition and also what it means in the context of the Ethereum network. Next, you will list down all of the functions which a token definition must include in order to comply with the ERC20 standard for Ethereum tokens. During the course, we covered the 6 functions and 2 events which must be implemented as part of the token definition, and it is the 6 functions which you need to recollect. Both of these topics were covered during this course, so please pause this video and then take some time to perform this exercise on your own. For the first task in the exercise, you needed to define a decentralized application. So in general terms, a DApp is an application which runs on a network of computers rather than on a single centralized machine. Such an architecture ensures that no single entity can control the entire application at any given point in time. How does this apply to the Ethereum world? Well, since Ethereum is an implementation of a blockchain network, all of the data which an Ethereum DApp will be using will reside on a blockchain, and the blockchain itself will be available on multiple nodes in the Ethereum network. Since the blockchain represents a decentralized ledger, an app which uses that blockchain is a decentralized application. Such an application, though, can be considered to have 3 different components, one of which is a web UI, and this is the part which most users of the application are likely to see. Behind the web UI, however, are the smart contracts, and it is within these contracts that the queries and transactions for the application will be defined. And finally, all of the transactions which are invoked via the web UI and the smart contracts will be recorded securely on the blockchain. From the point of view of the developers of these Ethereum dApps, it is the web UI and smart contracts which they need to build and focus on. For the last task in the exercise, you needed to recollect the different functions which need to be implemented in the definition of a token so that it complies with the ERC20 token standard for Ethereum. Now, the purpose of the ERC20 token standard is to define fungible tokens, which will provide a minimum level of functionality, enabling applications to use those tokens. One function which needs to be included in your token definition is for applications and users to know exactly how many of your tokens are currently in circulation. This is a value which is returned by a function called total supply. The function doesn't take in any arguments and returns an unsigned integer representing the supply of tokens. There are 2 functions which represent the ownership of tokens or the authority of someone to spend tokens. The first of these functions is called balance of, and this returns the quantity of tokens which are owned by a particular Ethereum account. It is the account address which needs to be passed to this as argument. While balance of represents direct ownership of tokens, it is also possible for someone to be delegated authority to spend tokens on someone else's behalf. To know how many of someone else's tokens a delegate is authorized to spend, you can invoke the allowance function. Now, in order to explicitly delegate someone else to spend tokens on your behalf, you can call the approve function, and this takes in as argument the address of the delegate for your tokens, along with the quantity of tokens they are authorized to spend. And finally, there are 2 functions related to the transfer of tokens from one account to the other. If you're spending your own tokens, then you can invoke the transfer function, and the arguments to this include the address of the recipient along with the quantity of tokens being transferred. And if you're spending someone else's tokens, you can invoke the transfer from function, whose arguments include the actual owner of the tokens, the address of the recipient, along with the quantity of tokens being transferred. During this course, we will be making use of the Truffle Suite in order to build out our decentralized application. And one of the tools in the Truffle Suite which we will now download is Ganache. Just as a reminder, Ganache is a tool which can help us set up a private Ethereum network, and it allows us to view the details of that network from a very intuitive user interface. So let us go ahead and download Ganache. So I'm just going to search for Ganache download here, and then click on the first link for me, which takes us to the truffleframework.com/Ganache URL. One thing to note is that the Truffle Framework is now one of the 3 tools available as part of the Truffle Suite. So the Ganache homepage is also available at trufflesuite.com/Ganache. Once you get there, there will be the option to download it for your own OS, and automatically it has detected my OS to be a Mac. So by clicking on this link, the installer for Mac will be downloaded to my file system. There are also Ganache installers available for Windows and Linux, so use the one which suits your system. If you're not using a Mac OS, you will need to perform the installation on your own. But if you are using a Mac, then you can just click on this link with me and then begin the download process. So I'll just fast forward this download and then bring it up in my file system. I'll just double click on this DMG file, and then the installation is rather simple. So this is just the standard macOS installation where I'll just drag and drop this icon into the directory. And then once it's available in applications, it can also be accessed from the Launchpad. So bringing that up and then clicking on Ganache. Since this is the first time Ganache is being opened, I'm being prompted to confirm that this is a trusted source. And once that is done, the Ganache dashboard is brought up. So in my case, this is version 2.0.1 of Ganache. And version 2 onwards, there are a few new features which have been added to the tool. It is now possible to set up multiple private networks in Ganache by creating them in different workspaces. And we can provision a new workspace from this UI. For now though, we will explore the Quick Start option, which will quickly provision a Ganache network in a workspace called Quick Start. So clicking on this, the network has been spawned, and we can view all of the accounts which are available by default. So if you have used Ganache before, these are 10 different Ethereum accounts with a balance of 100 Ether each. And you can see that the current block is now 0, which means that we are still at the Genesis block. This Ethereum network which has been created can be accessed by using this RPC server URL. So it's running on port 7545 of my local host by default. And as I'd mentioned earlier, this network has been created in a workspace called Quick Start. All the account related information is available here, including the account address, the Ether balance, and also the number of transactions which have been initiated from the accounts. We will now quickly explore the Ganache UI. So heading over to the Blocks tab, this is where each of the individual blocks in the blockchain can be accessed. And of course, as of now, there is just the Genesis block. In the Transactions tab, we will be able to view all of the transactions which have been recorded on this network. And again, this is blank for now because we haven't really used this network just yet. Switching now to the tab for Contracts. So this is a new feature which has been introduced in version 2 of Ganache, where it is possible to link a Truffle project to the Ganache network. And you'll be able to view the details of the smart contracts in that project from the UI. We will be covering this later on in this learning path. And we now move on to the other tab for events, which is also new in version 2.0 onwards of Ganache. So this is where the events which have been emitted from your Truffle projects will be visible. Heading now to the last tab for logs. And this is where the different interactions on your blockchain network will be logged. And this can get a little wordy, but you can see, for example, that the initialization of this network has been logged right here. So with a quick overview of Ganache complete, it is now time to provision the blockchain network which we will be using during the labs of this learning path. For that, we will create a new network in a new workspace, and we can do that from here by hitting the switch button. And this is where we will be prompted to switch to a different workspace. From this main dashboard, we will choose the option for a new workspace. And this is where we will need to specify the details of this new network we are about to provision. So here we will start off with the name for the workspace. And because the decentralized application which we will create is meant to serve as a fundraiser for a venture, we will call this network Fundraiser. It is possible for us to link some Truffle projects directly from this UI. However, we have not created one yet, so we will leave that as blank for now. And we'll instead head over to the Server tab. This is where we can configure details such as the host name, the port, and the network ID for the network. And we can also configure details such as the mining frequency, which has been set by default to auto mine. We won't be touching any of these settings and will instead head over to the accounts and keys section. And this is where we can configure each of the accounts which are generated. And we will once again leave these as the default so that 10 accounts with a balance of 100 Ether are generated. Moving over now to the chain section. Now, this is where details of the blockchain network can be specified, such as the default gas limit for the transactions and the default gas price. And we can also specify which fork of the Ethereum source code we wish to use. So there are 3 different options available as of this recording, and I'm going to stick to the version called Petersburg. Moving over to the Advanced tab, this is where you can set up logging and whether to use Google Analytics in order to track the usage patterns in Ganache. Again, we won't make any changes here and head over to the About section. And this confirms that the version of Ganache, at least for me, is version 2.0.1. Heading back to the first tab here for the workspace, if you are satisfied with all of the details which you have specified for your blockchain network, you can just hit the button to save workspace. And this has created a brand new blockchain network for us. And the workspace which this has been provisioned in is called Fundraiser. And with the blockchain network setup, we can import some of these accounts into the Metamask plugin so that we can use those accounts to submit transactions on the decentralized application which we will be building later on in this learning path. We have now set up our private Ethereum network using the Ganache tool. In order to begin using this Ethereum network from a tool such as Metamask, we will need to copy over this mnemonic phrase for the account addresses and then load that into Metamask so that all of the accounts will be imported into that tool. So just in case you're not familiar with it, this mnemonic phrase essentially maps to a set of Ethereum account addresses, which effectively translates to a wallet of Ethereum accounts. So now to load this into Metamask, I am going to copy this over and then bring up my web browser. And my browser already has the Metamask plugin installed, which I can access from this icon in the top right. If you do not have Metamask set up already, you will need to download and install it for your own browser. Metamask, at the time of this recording, is available for both the Chrome and Firefox web browsers. Metamask is a plugin which allows a decentralized applications UI, which loads into a browser, to access the Ethereum account which Metamask is connected to. This will allow a user to initiate transactions from their own Ethereum accounts from the UI of the decentralized application. So once we bring up Metamask, there is an option available to import existing Ethereum accounts into the Metamask tool using the seed phrase or the mnemonic phrase. So that is the option I'm going to choose right now. And this brings up a form where we can specify the seed phrase. So I'll just fill that in. And then after that, we will be prompted to enter a password for this Ethereum wallet, which we are loading into MetaMask. So I'll just fill in those details and hit the button to restore these accounts into MetaMask. So our wallet of accounts is now available in MetaMask. And the Ether balance appears as 0 here rather than the 100, which we saw in our Ganache network. And this is because we haven't yet linked Metamask to the network on Ganache. We will be doing that in just a little bit. But first, we can take a look at the menu here for Metamask. Here, you will observe that only one of the accounts from our Ganache network has been loaded into Metamask, and we will need to explicitly import each of the other accounts which we wish to use. Now, the reason why we are seeing an ether balance of 0 for this account is because we are now connected by default to the Ethereum main network. And by clicking on this, we have a collection of different networks which we can connect to, including a number of different test Ethereum networks, including Ropsten, Kovan, Rinkaby, and a new network called Guerli. To connect to our private Ethereum network, though, we are going to have to select the custom RPC option. And then in the form which appears, we will need to specify the RPC server URL for our Ganache network in the new RPC URL field right here. So heading over to Ganache, copying over the URL, and then pasting it back in Metamask, we can just go ahead and hit the save button, and the connection to our private Ethereum network has been established. So I'll just go ahead and close this form now. And this confirms that the 100 Ether available for this account matches what we saw in Ganache. So if you take a look at this Ethereum account address, which ends in F4D7, and then switch over to Ganache, it matches the first of these accounts listed here. So by default, when we imported the accounts using the mnemonic phrase, the first of the accounts from our network was loaded in. In order to test out the application which we are about to build, however, we will need to make use of additional accounts from this list. So to import the accounts explicitly into Metamask, we head back to the browser, and then from this menu for Metamask, we will click on the option to import an account. Once again, we will be given a form, and one of the ways in which we can import an account is by copying over its private key. To do that, we head back to Ganache, and clicking on this key button corresponding to the account we wish to import, the private key for that account will be available. So I'm just going to copy that over, head back into Metamask, and then we'll import this second account from our Ganache network into Metamask. So the second Ethereum account with the address ending in 4BFD has been imported into Metamask. But when we build our decentralized application, which will serve as a fundraiser for a venture, we will be simulating the crowdsourcing of funds for that venture. For that to happen, it is better to have a few additional accounts from which funds can be raised. And for that purpose, we will go ahead and import a couple of additional accounts from our network. So I'm just going to repeat the steps over here so you can just follow along with me quickly. So I'll just hit import. And then when prompted for the private key, we'll head over to Ganache, copy over the key of the third account as well, and import that into Metamask. So with 3 accounts loaded here, we can go ahead and load a fourth one as well. So I'm just going to repeat the same process. Import account, and then copying over the key of account number 4, and then pasting that into Metamask and importing account number 4's details. With the details now loaded for 4 different Ethereum accounts, we have enough for us to thoroughly test out the decentralized application which we are about to build. And if you wish to access and switch between the different accounts, you can just click on this menu. And for example, it is possible for us to switch over to account 3 right here. Now, if you wish, you can import additional accounts using the same mechanism from your Ganache network. But I'm just going to stick with the 4 accounts imported already, and we'll now switch over to account number 1 so that that becomes the default account when we load our decentralized applications UI into the browser. So at this point, both the Ethereum network setup on Ganache as well as the Metamask plugin in our browsers have been set up in order for us to use the decentralized application. And now, in order for us to begin coding that, we will make use of the Truffle Framework, for which we can bring up the shell on our operating systems. So I have brought up the macOS terminal here, but you will need to bring up your own shell. It is now time for us to begin coding up the backend of our decentralized application. This involves defining the smart contracts which will interact with the Ganache network which we have set up previously. And to do that, we will be making use of the Truffle framework. Before we proceed though, just a quick roundup of what a decentralized application is meant to do. This is meant to allow ventures to crowdsource funds for their projects. The venture will be able to set up an instance of a smart contract, which will allow individuals to contribute towards their project. And once the threshold of contributions has been reached before a specified deadline date, then the project is considered funded and the contributed funds will make their way to the venture. If the project deadline has been crossed and the required funds have not been raised by then the individuals who contributed towards it will be able to claim refunds. So let us now proceed with the coding of the backend, for which we will need to install the Truffle framework. This can be downloaded using npm. So if you don't have npm already, you will need to set it up. But once you have it, to install Truffle, you can run the command sudo npm install Truffle. And to make Truffle available globally, you can specify the -g flag. Once this is done, you can observe the version of Truffle which has been installed. In my case, this is version 5.0.19. And just in case you run into compatibility issues, I will just show you the versions of npm and node which I have installed. So in my case, the npm version is 5.6.0. As for the version of node, this is 10.15.3. So just note the combination of the Truffle, npm, and node versions in case you run into issues with compatibility. So now that the Truffle tool has been installed, it is now time for us to initialize our Truffle project. To do that, I'm creating a new project directory within my home directory. So this is called Crowdfunding. And once the directory is created, I'll just cd into it. And in order to initialize the Truffle project, we can run the command truffle init. So this will create a standard directory structure for a Truffle project, which will include separate directories for the contracts, the migration scripts, as well as the test scripts, and also a Truffle Config JavaScript file. So once we run this, our blank Truffle project will have been created. And we are also notified of the different Truffle commands which we can run in order to compile, migrate, and test out our contracts. So we can just confirm that all of the files and directories are being created by running an ls. And yes, the 3 directories and the config file which I had mentioned have been provisioned right here. Now, in order to begin the development process, I will switch out of the shell and then bring up this directory in my text editor. So I'm making use of the Sublime text editor, but you can use any other text editor or IDE which you're comfortable with for this purpose. We can quickly explore the contents of the directories here, starting with the contracts directory, and this includes a migrations.sol Solidity source file, which will handle the deployments for us. I won't be getting into the details of this, but just to summarize, this contract will be able to keep track of the last successful deployment script which was executed from the Truffle project. And when we perform a Truffle migrate, only the subsequent deployment scripts will be run. Moving ahead to the migrations directory, which includes the deployment scripts. This is where the deployment scripts are specified in a sequence. And number 1 in our list, and the only one at the moment, is the one to deploy the migrations contract to the blockchain network. Moving over now to the test directory, this is by default empty, and we will be setting up a test script later on. And then finally, when we look at the Truffle Config Js file, this includes a standard structure for the JS file, but there are no details populated here yet. This can be the first file which we modify. So I'm now going to clear out the contents here and paste in the new configuration for our Truffle project, which includes the networks to which the contracts in this project will be deployed to. So while we can specify a list of networks, there is just one which we wish to connect to, and that we will name Ganache. We will then populate the details of our Ganache network, which includes the host, which happens to be our local host, the port, which is 7545, the default gas limit, and then we also specify a wildcard for the network ID so that our Truffle project will connect to any network which is available on port 7545 of the local host. And with that done, we can save this file, but we will also modify its name to just be truffle.js. Once the renaming is complete, we will now head over to the contracts directory, where we will begin coding up the contracts which we require for the project. The first of these will represent some utility functions which we will use. So within this new blank file, I will go ahead and paste the contents of this utils contract. So once I have set it a name, which is utils.sol, we can go through the different blocks in this source file, starting with the pragma directive so that the Solidity compiler version is restricted to some variation of 0.5. And then following that, we define this to be a library rather than a smart contract. So this utils library includes two different functions. The first of these is called ether to way, and just as the name implies, this will accept as input an ether value and return its way equivalent. While we could use one of the Web3 util functions for this, this is just a little easier for us. So once we define this ether to way function, we will make use of another function in this library, and this is to convert minutes to seconds. This is because the crowdsourcing venture which we will set up will have an expiration time, and that time we would like to specify in minutes, but we will need to express it as seconds in the smart contract. So with both the functions in our library, we will be essentially converting from a unit which is easier for us to express to the unit which is required for the contract. So now with our library defined, we will go ahead and create one more file within the contracts directory. And this will be the main smart contract for our application. So I'll just go ahead and paste the contents of this contract, and we'll walk through the different blocks one by one. We make use of the same pragma directive here to restrict the compiler version to something between 0.5.0 but less than 0.6.0. And we also import the library which we just defined by making use of the import statement and specifying the location of our utils library. And following that is when we begin the definition of our crowdfunding with deadline smart contract. So here we explicitly specify the utils library which we wish to use so that the two functions will be available for us. And then we begin by defining 4 different states which the crowdsourcing project can be in. So these are ongoing, when the crowdsourcing is still happening, and then failed, which is when the deadline has expired and the required funds have not been raised, succeeded, when the funds have been raised before the deadline has passed, and finally paid out, which follows the succeeded state when the funds have been collected by the venture which put up the crowdsourcing project. Which takes us along now to the definition of the different events for our contract. And note that these events, when emitted, will be available for us to view in the Ganache UI. So the events here will correspond to the different actions which are possible in our contract. So for one, once the campaign has finished, then we will emit this event called campaign finished. And the published details include the address of the contract account representing the campaign, the total amount of Ether collected for it, and finally, whether the venture was a success. There is also an event which we emit when a contribution is made towards a venture. The contributing account address is published along with the contribution value, along with the current state of the venture. There is also an event which is triggered when the venture which initiated the crowdfunding has collected the funds, and this can be triggered following a successful campaign. And in the event where the campaign was a failure, then this withdrawn event can be triggered when the original contributors initiate a refund. We move along now to the different fields defined within our contract, as well as the constructor, starting with the name of the venture, and then we also specify a target amount, a funding deadline, both of which are expressed as integers. And then there is also the address of the beneficiary. There is also an address field for the owner of the contract, and we also make note of the state of the contract. This will need to be one of the values specified in our enum, which we saw earlier. We also make use of a mapping type in order to keep track of the contributions made by different participants in the venture. So here we map the address of the contributor to the amount which they contributed. We also make use of a Boolean variable to keep track of whether the target amount has already been collected, and the running total of Ether collected by the venture is tracked in this variable total collected. Following this, we define a modifier which will be used by this contract, and this is to check what state this contract is in. Many of the operations which we are about to define within our contract, such as contributing funds or withdrawing funds or refunding, will occur depending on the current state of the contract. And in order to check for that state, we have defined this modifier. We will be attaching this modifier to many of the different functions we are about to define, which takes us along now to the constructor for our contract. So when initializing an instance of the contract, which will represent a project which is being crowdfunded, we will need to specify 4 different arguments. The first of these is the contract name, which should be descriptive enough to suggest what this crowdsourcing venture is. There is also the target amount, which needs to be raised by the venture, and also the time by which that amount needs to be raised. The target amount is specified in Ether, while the duration of the contract is specified in minutes. We will be converting these to way and to seconds by making use of the library functions which we defined previously. And finally, when initializing the contract, we also need to specify the address of the beneficiary of the fundraising project. Moving ahead now to the body of the constructor. Here we initialize the name, target amount, funding deadline, and beneficiary fields in our contract, and note the use of the utils when we convert the target amount and the duration time. In addition to that, we also set the value of the contract owner to be the address of the individual deploying the smart contract. And then finally, we initialize the state of the contract to ongoing. So this initializes the different fields within our smart contract. And note that the fields which we haven't set any values for will be loaded with default values since there are no null values in the Solidity language. For example, the collected Boolean variable will be by default false, and the variable total collected will be 0. So now that we have defined the constructor for our smart contract, we will now move along to the different actions which are possible on the contract, and this depends on the current state of the contract. So here we have 3 different functions, and we will walk through them one by one, starting with the contribute function. So this is the function to invoke when an individual wishes to make a contribution towards the crowdfunding project. Note that this is defined as a payable function, which means that this function can only be invoked by attaching an Ether value to the transaction. That Ether value will, of course, match the contribution amount made by the individual towards the project. That Ether will be transferred from the account of the individual invoking this function over to the contract account representing the smart contract. So the contract effectively serves as an escrow until the end of the fundraising campaign. Now, a contribution can only be made towards a project if the contract happens to be in the ongoing state. So the contribute function cannot be triggered if the project has either succeeded or failed, for example. So while the inclusion of the in-state modifier performs one check for us, we include another check using another require clause here. And this is to ensure that an individual can contribute towards a project only if the deadline has not been exceeded yet. This check is performed by executing a function called before deadline, which we will define in just a little bit. But this will return a Boolean value depending on whether the deadline for the contract has been passed. If we are still within the deadline, this function will return a true value, in which case the code execution can proceed to the next steps. This is where we will update the amounts mapping structure to reflect the contribution made by this particular individual towards the project. So their address is added as the key to the mapping structure, and the contribution amount is added as the corresponding value. Note here that we are incrementing the value field here, which means that individuals can make multiple contributions towards the project, and their contribution amount will just be updated within the mapping structure. We will also update the total collected variable, which is a running total of the total funds raised until this point. Once those variables are updated, we will emit the contribution event, which includes the address of the individual making the contribution, the value of their contribution, and we will also pass along the current state of the contract, which is ongoing. And we pass this along as a string. And finally, we will perform a check to see whether the total amount of Ether collected is equal to or exceeds the target amount. If that is the case, then we will set the collected variable to true. Keep in mind here that we are not checking for the value of this collected variable when this contribute function is invoked, which means that individuals can continue making contributions towards a project even if the target amount has been exceeded. So now that we have defined the contribute function, we move along to the finish crowdfunding function, and this is the one which is called in order to end the crowdfunding campaign. We once again perform a check to see that the state of the contract is ongoing, and in contrast to the contribute function, this function can only be invoked after the deadline for the funding has been crossed. So once that condition checks out, we move along to the next steps, where we check the value of the collected variable. If this is false, which means that the crowdfunding target has not been hit, then we move this contract to the failed state, or alternatively, if the fundraising target has been met or exceeded, then we will transition this contract to the succeeded state. And finally, we emit the campaign finished event, which includes the address of this contract, the total value of funds raised, whether or not it exceeded the threshold, and also the value of the collected variable. That is, whether the campaign was a success or not. Another function which we now define is the one called collect, and this is invoked so that the beneficiary of a successful campaign is able to collect the Ether which has been contributed towards it. So with our in-state modifier, we ensure that the campaign is in the succeeded state, and if so, we call the beneficiary.send function in order to transfer over the total value of Ether raised by the campaign over to the beneficiary's account. We will then transition the state of the funding venture to paid out, and then we will also emit the collection event. If the Ether transfer to the beneficiary were to fail for some reason, then we transition the contract to the failed state. We move along now to the remaining functions in our contract, starting with the one to withdraw funds from the venture. This is a function invoked by the contributors towards the campaign once the campaign has failed and they wish to trigger a refund of their contributions. So we first perform a check that the state of this campaign is failed, and in the require clause, we perform a check to ensure that the one invoking this withdraw function has actually made a contribution towards this campaign. Once we capture their contributed amount from the amounts mapping structure, we will then zero out their contribution amount in that structure. This is done in order to prevent someone from claiming multiple refunds. So following that, we will invoke the send function in order to transfer over some ether from the contract account over to the one invoking this withdraw function. That is, we will refund the contribution made by the user from the balance in the contract account. However, if this send operation were to fail, we will update the amount mapping structure to reflect the original amount contributed by the individual. And finally, we will emit the withdrawn event to reflect the fact that a refund has been triggered from the contract. We now move along to some of the utility functions for this contract, starting with the one called before deadline. This is the one we called in the contribute function in order to check whether the deadline has been exceeded. And here we check that the current time is less than the time for the funding deadline. Now, current time is also a utility function, which we defined right here. And this simply returns the current time, which is accessible in the variable now. Though we haven't called this in the smart contract yet, in order for us to view the total value of ether collected for the fundraising venture, we define this getter for the total collected field. Another utility function, which we may not necessarily use, is to check whether a fundraising campaign has failed, and this will return true if the state is either ongoing or succeeded. And there is also one to check whether a campaign has been a success, and the condition for a successful campaign in this case is when the beneficiary of the campaign has been paid out the funds raised. So with that, we have now successfully defined the main smart contract for our decentralized application. So we can now go ahead and save it down. So I'm now going to call this crowdfunding with deadline.sol. And with the file saved, we can now proceed to the definition of the tests for our contract. Having defined this crowdfunding with deadline smart contract, it is time for us to define the deployment of our contracts and also set up the tests. To do that, we will now create one more smart contract within the contracts directory. And within this new source file, we will define a test instance of our crowdfunding with deadline smart contract. This is an instance of the contract which will only be used in the test script, which we will define a little later on. And the reason why we define a separate test contract is that for testing purposes, we need the flexibility to explicitly modify the deadline for the crowdfunding. This will allow us to test out scenarios where we try to perform a withdrawal of funds, for example, before the deadline, or try to make a contribution after the deadline has passed. So the flexibility to explicitly set the deadline will be useful in the tests. So I'll now go ahead and paste the code for this test instance of our smart contract. And we start off with a pragma directive, and we will be importing our crowdfunding with deadline source file. So this test version of the smart contract does in fact inherit from the original crowdfunding with deadline smart contract. However, it does include a field called time within this, and this is one which will represent the current time. This is the one which we will explicitly modify in our tests to simulate the passing of a deadline without having to wait until the deadline expires. So we start off with a constructor definition, and this mirrors the constructor for our original contract. And we will use the inputs to this constructor in order to instantiate a crowdfunding with deadline smart contract. So just to recap, the arguments are the contract name, the target amount specified in Ether, the duration of the crowdfunding campaign specified in minutes, and also the address of the beneficiary of the campaign. The body of this constructor in our test instance will be empty. One thing of note which we do here is to override the current time function which is defined in our original contract. So rather than returning the current time which is accessible from the variable now, we override it to return the time variable within this contract. This will ensure that the before deadline function defined within our contract will have access to this explicitly defined current time rather than the actual current time. And of course, we also need the option to explicitly set this value for the current time, which we have in this setter function. So this is all for the code of our test instance of the crowdfunding with deadline contract, where the main feature we have implemented is to allow us to explicitly define the current time so that we can simulate the passing of the deadline without having to wait for it to pass. So I'll just go ahead and save this file. And once that is done, all of the files in our contracts directory have been defined. So I'll just go ahead and close each of these files and then head over to the migrations directory. And this, of course, includes a deployment script for the migrations smart contract. So we can just make use of the source defined here already and then create one similar for the deployment of our own contracts. So I'm now going to create a new deployment script. And in the empty file, I'll just go ahead and paste the contents for the script to deploy both the crowdfunding with deadline and also the test version of that contract. So we start off by importing each of the artifacts which we require, which are the Solidity source files for not only the smart contract, but also the utils library. And then we deploy the utils library along with each of our smart contracts. And so that the contracts know where exactly to find the utils library, we also make use of the link method here so that we explicitly link the utils library to both the crowdfunding with deadline and also the test version of that contract to the deployed library. The use of the await keyword will ensure that the library has been fully deployed before it is linked to either of the smart contracts. So this script takes care of the deployment and the linking of the utils library. So we can go ahead and save this. And since the deployment scripts defined in the migrations directory follow a sequence, we can ensure that this deployment occurs after the deployment of the migrations contract by assigning to this a deployment sequence of 2. So by calling this 2_deploy_utils.js, we ensure that this is the second deployment script to execute. And we also convey the fact that this will deploy the utils library. So with this saved, we will now create another deployment script. And this will, of course, deploy our crowdfunding with deadline smart contract and initialize it. So I'll now go ahead and create a new file and then paste the contents of our new deployment script, where we begin by importing the artifact which we require, which of course is our Solidity source file for the contract. And then we deploy and initialize this crowdfunding with deadline smart contract, which represents a new crowdfunding campaign. The arguments to the deployer.deploy method include the name of the contract instance being deployed, followed by the arguments to its constructor. Our first argument is the name of the contract, which we specify in the string fundraiser. The second argument specifies that the crowdfunding target is 40 Ether. The third argument denotes that the duration of this campaign is 30 minutes. And the last argument here is the beneficiary of this campaign. And this is now a blank string. But in order to populate it, we will be loading it with one of the Ethereum account addresses from the Ganache network. But for now, we can just go ahead and save this deployment script. And I'm calling this 3_deploy_contract.js to denote that this deployment will follow the deployment of the utils library and that it deploys our main smart contract. So once we save this, we can head over to the Ganache UI, and then I'm going to pick the fourth of the accounts in this list to be the beneficiary of the first crowdfunding campaign which we will simulate. So I'll just copy this address ending in F972 and then paste it as the last argument when we instantiate our smart contract. So just to summarize, our crowdfunding campaign will be to raise 40 Ether in 30 minutes, and the beneficiary of this campaign is the fourth account in our list of Ethereum accounts on Ganache, which in my case is the one with the address ending in F972. So at this point, we can just close down each of these migration scripts and then head over to the test directory where we will define the tests for our smart contracts. With the smart contracts as well as the deployment scripts for our Truffle project defined, we will now move along and then create a test script. So within the test directory, I'm going to go ahead and create a new file. And this will be a JavaScript file and will make use of the Moca testing framework in order to define the tests which will be performed on the smart contract. The Moca testing framework includes a number of functions and hooks which allows us to structure our tests. So for example, we can have a number of test cases which are grouped together into test suites, and then we can make use of hooks in order to perform operations which are common to each of them. So I'm now going to paste the contents of the test script and then walk through each of the blocks one by one. We start off by importing an instance of our test smart contract. So this is the one where we can configure the expiration time for the contract. This is followed by the definition of a test suite, for which we make use of the contract function. If you're familiar with the Moca testing framework, the contract function here is similar to describe in Moca, within which you can aggregate a number of test cases and also some of the common operations for each of them. But in addition to the features of the describe function, the contract function makes available for us the clean room features of the Truffle framework. This ensures that each time the contract function is executed, the contracts will be redeployed and the tests will be run with a clean contract state. In addition, the contract function also returns a list of accounts which is made available by the Ethereum client, and this is what we capture in the callback function. So within the definition of our callback, we initialize a variable called contract, and then we also create variables for the contract creator and the beneficiary, which we will be using when we create instances of our smart contract within the tests. Do note here that the addresses for the contract creator and beneficiary are accessed from the accounts variable. This is what the contract function in a Truffle test makes available for us. Moving now to the fields defined within our tests. So here we create a constant called 1 ether to represent a single ether in terms of way. Just as a reminder, 1 ether is 10 to the power 18 way. We also create a constant for an error message, and then we define numbers for each of the possible states for our contract. That is, each of the states for the fundraising campaign: ongoing, failed, succeeded, and paid out. So we will have a number of different test cases defined within this test suite. And before each of those test cases are executed, we will be creating a new instance of our smart contract. We use the Moca before each function for this purpose. So here we initialize our crowdfunding with deadline smart contract by giving it a name of funding. The target amount for the fundraising campaign is 1 ether, and the expiration of this campaign is 10 minutes or 600 seconds. The beneficiary of the fundraiser is the account address available in the beneficiary variable. So when we create an instance of our contract, we will be invoking a transaction, and we need to define the address from which this transaction will be triggered. Here we specify the address in the contract creator variable, and we also set a gas limit of 2 million Wei. So this will deploy an instance of our smart contract, which of course has a target fundraising amount of 1 Ether, and this needs to be raised within 10 minutes. Given this contract instantiation is done within the before each function, a new instance of the contract will be available for each individual test case within this test suite. We now proceed to defining each of the individual test cases. And the first test case is to check whether the contract has been initialized according to our specifications. We make use of the it function for Moca, which defines an individual test case. And thanks to the definition of the before each function, this test case will have a deployed instance of our crowdfunding with deadline smart contract available in the contract variable. So there are a number of different checks which we perform within this test case. Firstly, we check that the name of the contract has been initialized correctly. So we access the name field in our contract, and then we invoke the call method on it in order to retrieve the contract name. And we use the chai assertion library to say that we expect this contract name variable to be equal to funding. So this confirms that the value passed as the first argument to the constructor of the contract, which is funding, has been assigned to the name variable of the contract. Next, we verify that the target amount has been set correctly. So we query the target amount field of the contract, and then once again use the chai assertion library to assert that this target amount is equal to 1 Ether. The next thing we do is to check that the funding deadline property has been set to 10 minutes or 600 seconds. And once again, we make a call to the funding deadline property and then make use of the chai library in order to ensure that it is equal to 600 seconds. We then check that the beneficiary field in the contract has been set to the beneficiary which was passed as an argument to its constructor. And then finally, we ensure that the state of the fundraising campaign or the state of the contract is ongoing. So this test case essentially performs 5 mini tests where we check that the values which were passed to the constructor of the contract have been assigned to the correct fields of the contract. And we also check that the state of the contract has been initialized correctly. So that concludes the first of many test cases in our test script. And the second of these is to ensure that the contribute function works exactly as expected. Here we make a call to the contribute method of our contract, where we pass along a value of 1 Ether, and this transaction will be initiated from the contract creator's address. We then ensure that the contribution has been recorded correctly in the amounts mapping structure, where we retrieve the value corresponding to the contract creator's key, and we expect this to be equal to the amount contributed, which is 1 Ether. We also ensure that the value of the total collected field within the contract is equal to 1 Ether in this case. So now that 2 out of the test cases are complete, we move along to number 3. And this is where we wish to ensure that no contribution can be made to the fundraising campaign after the deadline has passed. Now, a new instance of the contract will be available to this test case. And rather than wait the 10 minutes which we specified as the expiration for the contract, we can now make use of the set current time method defined within our test smart contract instance in order to effectively fast forward 10 minutes. So here, we set the current time value to 601, which is 1 second past the 10-minute deadline. Following that, we will invoke a transaction, and this is where we pass along 1 Ether from the address of the contract creator. Note that in this case, we are triggering the fallback function of the smart contract, which has not been defined, which is why we expect that this operation will fail, which we check for using the Moca library. You can also invoke a call to the contribute method as we did in the previous test case, and you can also expect that operation to fail. Moving along now to the next test case, where the aim is to play out the scenario where the crowdfunding operation is a success. We start off by contributing a value of 1 Ether to the crowdfunding campaign, which is of course the target amount. And then following that, we fast forward past the expiration time for the contract by calling the setCurrentTime method. And then we invoke a call to the finish crowdfunding function within the smart contract. This function will check, first of all, that the crowdfunding deadline has passed, and secondly, whether the target amount has been raised. If yes, it will change the state of the contract to the succeeded state, which is what we are checking for in the expect statement. In the previous video, we started off defining our test script and already covered a few test cases within the single test suite which we have defined. The next test case is to play out the failed crowdfunding campaign scenario. So here we don't make any contribution at all, and then fast forward past the expiration time and then call the finish crowdfunding function. This should return a value of failed state since the required funds have not been raised, and that is what we check for right here. Scrolling further down, there are 3 further test cases which we define within this test script. The first of these is to ensure that in the event of a successful crowdfunding campaign, the beneficiary is credited with the Ether which has been raised. To do this, we first make a contribution of 1 Ether from the contract creator address, fast forward past the campaign deadline, and then call the finish crowdfunding function. Following that, we first initially get the balance of the beneficiary's account in the init amount variable, and we then trigger a call to the collect function in our contract. This should transfer over all of the collected funds, specifically 1 Ether, to the account of the beneficiary. Following this, we check the account balance of the beneficiary's account once more, and then verify that this is 1 Ether more than the balance when we checked it previously. That is, the difference between the new balance and init amount variables should be 1 Ether. Note here that we are retrieving the balance of an Ethereum account using the web3.eth.getBalance method. In addition to checking the Ether balance of the beneficiary, we also verify that the state of the contract, that is the state of the fundraising campaign, is paid out. Moving now to the next test case. This is where we verify that our refund mechanism has been set up correctly. So after contributing a little under 1 Ether to the fundraising campaign, we will fast forward and then finish the campaign. And then following that, we will initiate a call to the withdraw function. And then we verify that the value of the contributions recorded in the amounts mapping structure is equal to 0 for the contract creator. Note here that we are not checking the Ether balances in this case, because there will always be a minor variation in the balance depending on the gas cost incurred for the transactions. And finally, we have a test case to verify that an event has been emitted. So we don't make any contribution to the fundraising campaign. We then fast forward past the deadline and call the finish crowdfunding function. And then we access the transaction logs, where we verify that the number of events which have been emitted is equal to 1. Following that, we retrieve the details for the event and confirm that the value of the total collected property for that event is equal to 0. That is, we verify that no contribution was made to the campaign. So that is the last of the test cases. And we have now defined all of the tests for our smart contract, and we have grouped them all together into a single test suite. We can now go ahead and save this test script. I'm going to call this test.js. And once that is done, we can in fact go ahead and run these tests. So I'm going to bring up the shell, and the command to execute is truffle test. And the arguments to this will be the network on which the test will be performed. This network will, of course, need to be defined within the Truffle config file. And we have one called Ganache, which of course points to our own private Ethereum network provisioned on Ganache. So when we run this command, firstly, all of our smart contracts will get compiled, and then following that, they will be deployed over to the Ganache network, and each of our individual tests will be executed. From the output, it is clear that all of our test cases have passed. This confirms that all of the logic defined within our smart contract have been set up correctly. So within our tests, there were multiple deployments of the smart contract, and then we also invoked several transactions within the tests themselves. To see what exactly has been recorded on our blockchain network, we can bring up the Ganache tool, and by looking at the current block index, it becomes clear that 32 additional blocks have been added to the blockchain. When we took a look at our Ganache network before we created and deployed our tests, we were still at the Genesis block, which was block 0. Not only have new blocks been added to the blockchain, even the Ether balances of the two accounts which we used in the tests have been affected. The first account here was the one which we specified as the contract creator, and this was the one which we used for all of the transactions which were initiated within our tests. We also made contributions to the crowdfunding campaigns from this account, and that is reflected by the Ether balance here, which is a shade under 97 Ether. So while this account was used in order to contribute towards the crowdfunding campaign, the beneficiary of the crowdfunding was this second account in the list. There was exactly one test case within our test script which paid out the funds over to the beneficiary, and that is reflected by the 1 Ether increment in the balance of this Ethereum account. So now that we have seen how the accounts have been affected and also the length of the blockchain, let us go ahead and take a look at the blocks themselves. So here we can see all of the 32 blocks which have been mined on the blockchain network. You will observe that each of these blocks has exactly one transaction, and that is because we had set the blockchain network to auto-mine. That is, to process the transaction and add it to a block as soon as it is invoked. To examine the details of the latest block, we just click on it. And this tells us, for example, how much gas was used by all of the transactions in this block. That is the one transaction. We can also view the account from which this transaction was invoked, which is the contract creator address, which of course we used for all of the transactions in our tests. And also the to contract address represents the address to which the smart contract was deployed. When we click on this transaction data, we are navigated to a broader view of the transaction. So we can just head back from this view, which takes us to the block view. And then heading back from here, we can view all of the blocks once more, and we head over to the Transactions tab. The transactions whose details we just saw is available at the very top over here, and we can confirm that it is the same by clicking on it. So yes, the details are exactly the same. From here, we can head back to the Transactions view, and then from there, we head over to the Contracts tab. So while our test script performed multiple deployments of our smart contract over to this Ganache network, the contracts which will be visible in this view need to be loaded from a Truffle project over to this UI, which is why we don't see anything here. Heading over to the Events tab, we see no events recorded here. And again, this is because the events will only be loaded from those contracts which have been explicitly linked to Ganache. Heading over now to the Logs tab, you can scroll through this entire list to view the details of the transactions which have been recorded here. We won't be doing that, however, since there are just too many logs for us to go through. In the previous video, we saw that there was no information available either in the Contracts tab or the Events tab of the Ganache tool. Those tabs can only be populated if we explicitly link one of our Truffle projects over to Ganache. That is precisely what we will do in this demo. So we now click on the Contracts tab over here. And as we expect, there are no contracts visible, but we do have the option to link an existing Truffle project. So when we click on this button, what comes up is the configuration of our workspace. So we saw when we set up our fundraiser workspace that there is this option here to link Truffle projects to the workspace, that is to our blockchain network. We decided to forego that option previously, but let us go ahead and add our own Truffle project right now by clicking Add Project. We will need to navigate in our file system over to the location where the truffle.js or Truffle Config Js file is located. So I'm now here in this Truffle project directory and will select the truffle.js file which we had set up earlier. This, of course, contains the definition of the only network for our project. And once this is selected, we will load it into our blockchain network. And do keep in mind that we can use this interface to add multiple projects over to our network. But once all the projects have been loaded, we can click on this button to save and restart. Once that is done, we are navigated automatically to the Accounts tab. And to view whether the contracts are now visible, we click on the Contracts tab. On this occasion, we do see some data here. And the name Crowdfunding, which we see here, is the name of the directory for our Truffle project. But we do see this message that rich contract data will only be visible if we happen to compile the sources in our Truffle project. That is exactly what we will be doing a little later. But before that, we head over to the Events section. And then we see some data over here as well. Now, if we navigate to one of these events and we just go ahead and click on them, what we observe doesn't really convey too much information. So this is an event which was emitted by our Truffle project, but we get this message that to see rich event data, we will need to link a Truffle project. So if we head back from here and then click on another event, we see a similar view. We don't really see too many details of the event itself. So clearly there is more to be done if we wish to view the details of the events in this view. So clicking on the back button here, we are navigated to the list of events. And I'm now going to head over back to the Contracts tab. And as the instructions convey, we can go ahead and compile the sources in our project in order to see what exactly is visible within the Ganache UI. In fact, what we will be doing is to run the Truffle Migrate command, which will execute each of these three deployment scripts which we have defined. But before that, it will run the Truffle Compile command in order to build any of the uncompiled smart contracts. So just to recap what will be deployed, we have this initial migration.js, which will deploy the migrations contract. There is the second deployment script, which will deploy the utils library. And then there is a third deployment script, which will deploy and then initialize our crowdfunding with deadline smart contract. This will be initialized with a target fundraising amount of 40 Ether, and this will expire within 30 minutes. The beneficiary address is the fourth account listed in our Ganache network. In my case, this has the address ending in F972. So I'm going to close this out and then head back over to the shell where we can execute the command Truffle Migrate. Once again, we specify the network to which this migration will occur. And this is, of course, the one network defined in our Truffle config file, which is Ganache. So this will first run a Truffle compile, followed by executing each of the deployment scripts in sequence. So when we run this, a lot of output is generated. So I'm just going to scroll back up. We can see at the top that all of the contracts were compiled using version 0.5.0 of the Solidity compiler. The migrations occurred to our Ganache network. And the first migration script was executed to deploy the migrations contract. Then the utils library was deployed. And then finally, our crowdfunding with deadline smart contract. The full details of each of those deployment transactions are visible here. Now let us head back to Ganache and view the effects. We are now in the Contracts tab, and if we take a look at the current block, we observe that 6 additional blocks have been added to the blockchain network. Now heading over to the Accounts tab, we observe that the Ether balance of the first account has dropped just a little more. But the main thing for us to observe is in the Contracts tab, so we head over to that, and we see a little more information here. So while we would have expected 3 different contracts to appear here, there are in fact multiple occurrences of each contract. For example, if we take a look at this particular instance of our crowdfunding contract, it says that the contract has not been deployed yet. It is possible that by the time you view this video, some update would have been made, in which case you may see something different. But in order to view the details of the actual deployed contract, we can click on one of these instances here, and you will notice that they seem to be duplicates. And this gives us the actual information of our deployed smart contract. You can view the address to which it has been deployed and also the balance of Ether in the contract account. And within the storage section, we can view the values of each of the fields defined within our contract. So we can see who the beneficiary is, the funding deadline, the name which we set to the contract, as well as the owner, state, target amount, and so on. There are no transactions or events which have been recorded for this particular contract. And now if we head back from here, we can examine the details of the migration contract which was deployed. So once again, this has an Ether balance of 0, but we can see that the last completed migration was number 3 out of the 3 deployment scripts in our migrations directory. And this is how the migrations contract keeps track of the latest deployments. All of the transactions associated with this contract are also available here, and we can click on one of them to view the exact details. I won't be checking that now, however, and will instead head back. And from here, we can proceed over to the Events tab. Now things do look a little cleaner on this occasion since we only see 3 encoded events. So we can just go ahead and click on one of them. And once again, not too much information is available. You will recall that the event details are only available when we emit them from within the transactions of our smart contract. And we have not invoked any such transactions since we loaded this project into Ganache. We will be doing that though a little later in this learning path. In this exercise, you will first describe the features of Ganache. So Ganache is one of the tools which is available in the Truffle Suite, and we saw during this course that this can be used in order to set up your own Ethereum network, which can be used for both development as well as testing purposes. However, you will need to describe what exactly the features are of Ganache which make it ideally suited as a sandbox environment in which to deploy your contracts. For the next and last task, you will list down the different steps involved in the life cycle of a project in the Truffle Framework. In addition to Ganache, another tool available in the Truffle Suite is the Truffle Framework. This is mainly used to manage the life cycle of your smart contracts, and you will now need to recollect exactly what the different steps are in this life cycle. Since both of these topics were covered during this course, please pause this video and spend a little bit of time to perform these tasks on your own. For the first task in the exercise, you needed to list down the different features of Ganache, which of course is the tool which we used in order to set up our own Ethereum network. So not only is Ganache used to set up a private Ethereum network, but it can in fact be used to set up multiple Ethereum networks, each of which are configurable. The isolation of each of the networks is made possible by the setting up of separate workspaces, And Ganache makes it very simple to switch between the different Ethereum networks by simply switching the workspace. Each blockchain network set up on Ganache comes with a number of accounts, each of which have been preloaded with Ether. By default, 10 accounts are set up in each network, and each of these are loaded with 100 Ether, which is more than enough in order to deploy multiple contracts and to perform multiple interactions involving transactions. Once you have set up blockchain networks from Ganache, you can also make use of its very intuitive user interface in order to view the details of your network. The information which you can view from Ganache include the blocks which make up your blockchain network, the transactions which are recorded on those blocks, the events which are emitted from calls to your contract, and you can also view details of your contracts themselves. This includes all of the state variables for your contract and also the Ether balance for your contract accounts. You will also be able to view all of the transactions and events which are associated with a specific contract. Now, all of these features make Ganache very useful when it comes to development and testing, since all of the details which are available in the UI will allow you to very quickly debug your smart contracts. However, another powerful feature of Ganache is that many details of the blockchain network itself are configurable. Some of the configurable properties include the mining frequency, so that you don't need to wait several seconds for a particular transaction to be processed and mined. You can also configure the Ethereum accounts which are provisioned in the blockchain network, either by specifying your own mnemonic phrase, and you can also control the Ether balance of the accounts which are set up. With these and other network configurations, you can set up your Ethereum network to be either very similar to the main network or one which is very different and is specifically suited to your own development needs. Moving along now to the next task, which was to list down the different phases involved in the lifecycle of a Truffle project. This refers specifically to the Truffle Framework rather than to the Truffle Suite as a whole. But in order to start the development of your smart contracts, you will first need to initialize a Truffle project. So within a blank directory, you can set up such a project by running the command truffle init. This will create a standard directory structure which includes separate directories for your contracts, your deployment scripts, and your test scripts. There is also a Truffle config file in which you can define, among other details, the networks to which your contracts can be deployed. Now, once your project has been initialized, it is up to you to develop your project sources. These sources will include the smart contracts themselves, but if you'd like to follow the best practices for developing these contracts, then you will also need to build out your own test scripts. We saw during the course that a test script can be written using JavaScript, and it can make use of the Moca testing framework. Now, once you have automated the tests for your project, you can also automate the deployment of your contracts, and you can define your deployment scripts within the migrations directory. So this concludes the second phase of your project's lifecycle, and we will move along now to the next phase, which is to build your project. This is as simple as running the command truffle compile from the root project directory. This will generate a number of build artifacts which will be set up in the builds directory of your Truffle project. So once you have built out the sources, it is time for you to run the tests. And to run all of the tests defined in the test directory, you can execute the command truffle test. It is also possible to run individual test scripts rather than all of them, where you follow truffle test with the name of the script to execute. And after your project sources have been built and your tests have run successfully, it will be time for you to deploy your contracts to an Ethereum network. And in order to execute the deployment scripts which you have set up in the migrations directory, you can execute the command Truffle Migrate. So at this point, your smart contracts have been built, tested, and then deployed. and you can consider that it has gone through all phases of its life cycle. In the previous course of this learning path, we built out the backend for our decentralized application, which allows someone to crowdsource funds for a venture. In this course, our focus will be to develop the front end for that application, for which we will be building a UI using JavaScript. We won't be building this UI from scratch, however, since we can make use of some JavaScript libraries to make our job much easier. One of these is the React library, and this includes a lot of components for us to build interactive user interfaces. The second library we will be using is Drizzle, and this is one of the tools in the Truffle Suite, and this allows us to integrate the front end of our application with smart contracts deployed to an Ethereum network at the backend. The backend artifacts which we will be linking to the web UI for our app are available in the build directory of our crowdfunding project workspace. So this is something which I have brought up in my text editor. And in order to view exactly what it contains, we can click on this, which reveals a directory called contracts. And when we expand that, we can see 4 different JSON files. These correspond to the 3 smart contracts as well as the utils library which we created within our Truffle project. And if you want to view the details of our crowdfunding with deadline smart contract, for example, we can click on this JSON, and we observe that we have all of the details of our smart contract right here. This includes the ABI for the contract, and just in case you're not familiar with it, ABI is short for Application Binary Interface. This includes a lot of metadata for the different fields and the functions in our contract, and all of this information in the ABI can be used by any application which wishes to interact with our smart contract. This JSON file also includes details such as the contract metadata, the Ethereum bytecode, which will enable the execution of the contract code, and very importantly, once the contract has been deployed, this JSON file will also include the address on the Ethereum network to which that contract has been deployed. So how exactly does this involve the development of the front end of our application? Well, the front end needs to know where exactly the back end is, and the information for that is all available in this JSON file, including where exactly the contract is deployed on the Ethereum network, as well as all of the ABI information which is needed in order to interact with that deployed contract. If we head over to the migrations contract now, we will see similar information right here, including the ABI for the contract. And scrolling further down, there is also a section for the networks right at the bottom, where we can see the address to which this migrations contract has been deployed. Heading over to the next contract for the test crowdfunding with deadline, we see similar information. And finally, when we take a look at the utils JSON, we see once again some ABI definition. And scrolling right to the bottom, we will be able to view where exactly this has been deployed in the blockchain network. So we now know that the web front end which we are about to build for our decentralized application will need access to these JSON files within the build directory of our Truffle project. So let us go ahead and set up the front end application. And for that, I'm heading back to the shell. And from within the root of our Truffle project directory, we can download a node package which will allow us to create a template React application which we can build upon in order to code up the front end of our dApp. So the command to execute is npm install create-react-app, which we do with the -g flag so that it is available globally. So when we run this, that npm package has been installed, and we will now go ahead and use that in order to create an application called client, and this will be set up in a different directory called client within our Truffle project directory. So when we run this, a template React application will be created within the client subdirectory here. And this will, of course, go ahead and download a lot of sub packages which are required. And this might take a while, so I'm just going to fast forward until everything has been installed and our template client application is now ready. Just to take a look at what exactly has been installed, I'm going to bring it up in my text editor and then expanding this client directory. You will see that this is a node project, and we can expand the public directory next to see what exactly it contains. So there is a default index.html which has been implemented, and this is something we will need to modify a little later. But now that we have a default React application, the next thing we need to do is to install Drizzle. To do that, I'm going to navigate from the shell over to the client subdirectory, and then from here, we'll install Drizzle locally. Drizzle is not the only package we will be installing though, since we will also be installing the semantic UI React libraries. So both of these packages will be installed and then saved locally. So we can just go ahead and run this command. And this again could take a really long time. So I'll just go ahead and fast forward until the installation is complete, which means that we have now successfully installed Drizzle and also some additional React libraries. At this point, let us cd into the source directory of the standard React application, and then we can run an ls just to view exactly what its contents are. We already saw previously that there was an index.html which was available, and now we see some standard CSS and JavaScript files right here. So all of these files will be used, and we will be modifying many of them later on. But what we really do need for our client application are the build artifacts generated in our Truffle project. So these are all of the JSON files which were available for our deployed contracts. And to make it available to the client, what we will be doing is to create a symbolic link so that all of those JSON files will be available within the source directory. So now I'm setting up this symbolic link using the ln-s command, and this will create a subdirectory here called contracts, which will map to the build/contracts directory from the root of our Truffle project. So we can just go ahead and run this and do an ls. And in addition to the files we saw previously, this contracts subdirectory is available here. And when we cd into that and then run an ls, what we see are the 4 JSON files which we had taken a look at just a little earlier. So with the steps which we have just performed, the backend of our decentralized application, which includes the deployed smart contracts and the ABI needed to interact with it, is available for this front-end application. We have yet to code this application though, which is what we will begin to do in the next video. For now though, I'm just going to cd up one directory so that we will be in the source directory of our client application. Having set up a standard React application and also having installed Drizzle on our machines, it is now time for us to begin coding up the front end of our dApp. I have brought up the Truffle project directory in my text editor, and within the public directory of the client application, there is this index.html. When we bring it up, we can see that this represents a default React application, and this uses the index.js file defined within the source directory as the entry point for the app. Now, these contents we can get rid of now, and we will go ahead and paste the HTML for our own crowdfunding application. So we set a title of crowdfunding application for our homepage, and then following that, within the body of this page, we define 2 different divs. One has the ID root and the other has the ID campaign. We will be populating these divs from the other source files in our client application. And for that, we can now head over to the source directory. And when we expand that, we view these JS and CSS files here. And the first file which we will edit is app.css. So this includes style definitions for many different components in the web page. But again, we can just get rid of all of this. And we will paste in our own CSS definitions here. So this is where we configure the style of the app component of our application. So just to quickly go over what we have defined here, we have specified a margin width and also the text alignment. So this applies at the top level. At the level of the header, we specify a background color as well as the default height and padding. And we also configure the style for the title and the intro. Moving along now to the index.css file. Once again, there is a standard definition here. This is something to configure the body in our HTML. And I'm only going to make one minor change here, where I'll adjust the margin width to 10 from the default of 0. With that change made, we can save down the changes to index.css and then close down this file. And then also save down app.css and close that as well. We can now move along to the index.js file, which will be the entry point for our application. So you'll see that once again, there is a default implementation, but we need to clear this out once more. And I'll paste in the contents of our new index.js. We begin by importing all of the components which we will require. This includes the React and React DOM components. And we will also be importing our index.css and also app.js. We will be modifying the app.js file as well. And following that, from the Drizzle package, we will be importing the Drizzle class and also the generate store function. The Drizzle libraries will store the state of the smart contract in a Drizzle store, and this store can be created using the generate store function. A Drizzle instance will be created out of this Drizzle class and also the Drizzle store, and this is something which will be passed down to each of the child components from root component of our application, so that all of the child components will have access to the state of our deployed contract by means of the Drizzle store. We also import the JSON of our deployed crowdfunding smart contract right here. And then following that, we will print out the JSON contents over to the console and then create an options object out of the JSON of our deployed smart contract. We will then create an instance of a Drizzle store using the generate store functions, whose argument is this options object which we have just created. This will create the store from which we can access our smart contract state. And then finally, we create a Drizzle instance using both the Drizzle store as well as the options object. And this Drizzle instance will be passed along to the app component. So this is a component which we render from this index.js file. And this also happens to be the root component of our React application. Since we have passed along this Drizzle instance to the app component, it will have access to a smart contract. And not only will the Drizzle instance give access to the variables within the smart contract, but it can also be used in order to invoke the functions and trigger transactions. We now move along to the app.js file, and this is where we will define the app component of our React application. So I'm just going to go ahead and clear the current contents of the file and then paste in our own code. And then scrolling all the way to the top, we can walk through each of the steps one by one. So we begin by importing the React and component classes from the React package. And we also load the app.css file along with the campaign.js file, which we are yet to define. We then begin the definition of our app component, which includes an object called state, which will be used to store two state variables. The first of these is called loading, and this is by default set to true, and it indicates whether Drizzle has finished initializing and the application is ready. The other state variable is the Drizzle state, and this is where we will store the actual state of the Drizzle store. That is, the state of our deployed crowdfunding smart contract. This is followed by the definition of the component didMount function, which is what is invoked when this app component has been successfully mounted. So we start off by importing the Drizzle instance, which was passed to this app component, and this is accessible from this.props. And then following that, we make a call to the Drizzle store's subscribe function. The argument to the subscribe function is callback, which we are just about to define, and the value which is returned by the subscribe function is captured in a state variable called unsubscribe. We will be referencing this unsubscribe variable just a little later. We now move along to the definition of our callback function, and this is something which is called whenever the Drizzle store is updated. That is, whenever a contract state has been changed. And what do we do when the contract state has changed? Well, we first capture the state of the contract by making a call to drizzle.store.getState, and we follow that up by checking whether Drizzle has been initialized, and if it is, we set the loading state variable to false. And we also update the Drizzle state variable to the actual value of the Drizzle state. The state update will occur by calling the function this.setState. So once the app component has successfully mounted, we will set up this subscription, which will update the local Drizzle state variable with the latest contents of the contract state. So when we set up that subscription in the component didMount function, the value which was returned was a function which can be called in order to unsubscribe from that subscription. So when our app component will unmount from the tree, then we can call this.unsubscribe method, and then this will end the subscription which we had instantiated in order to update the local Drizzle state variable with the latest state of the deployed contract, which moves us along now to the render function. And here we begin by checking the value of the loading state variable. So if the component is still loading, then we return the text loading Drizzle. And when the loading is complete, we render the app component, which includes a div followed by a header, which says that this is a crowdfunding application. And then this includes a campaign component to which we pass along the Drizzle instance and also the Drizzle state. The campaign component is something which we will define just a little later in a campaign.js file. So we now end the app.js definition by exporting the app module. In the previous video, we defined the app component of the front end of our decentralized application. The app component happens to be the top level component in our front end app, and it does not directly interact with our deployed crowdfunding smart contract. Those interactions will be handled in the next component which we will create in this video, and that is the campaign component. When I say that the app component does not directly interact with the deployed contract, what I mean is that it does not perform any query operations or invoke transactions on the contract. However, we did set up a subscription so that the app component always has the latest version of the contract state, and we also ensure that it gets passed down to the campaign component. We can now begin coding up this campaign component by creating this new file in the source directory, and once that is done, just as before, I will paste the entire contents of this file and then walk through each of the blocks. We begin by importing the React and component classes from the React module, and then after that, we import some of the UI elements we will use in our web page from the semantic UI React package. These include the button, input, and table classes. Since we will be displaying the details of the fundraising campaign within a table, we will accept input from the user, such as the campaign contribution, for example, in an input. And in order to invoke transactions, such as submitting contributions, we will be making use of buttons. So we can now begin the definition of this campaign component, where we start off by defining the 4 different states of a campaign. These correspond to the 4 states which we defined within our smart contract, which are ongoing, failed, succeeded, and paid out. As for the state variables for this component, we define an object called state, which in turn includes an object called campaign, and this contains a lot of the campaign-related information. The name of the campaign, the target amount, the total amount of funds collected, and these you will observe correspond to the different fields within a smart contract. While these are all campaign-specific information, we also store a contribution which has been made by an individual in the field contribution amount. This field will allow us to display to an individual connecting to our website what exactly they have contributed towards the campaign. We will now set about initializing this campaign component in the component didMount function. We first get access to the Drizzle instance which was passed down from the app component, and this is available in this.props. And we also use the Drizzle instance in order to get an instance of our deployed crowdfunding with deadline smart contract. So once we have the contract instance, we will be able to retrieve each of the properties within the contract in order to populate each of our state variables for the campaign component. This includes details such as the beneficiary, the deadline, and the state of the contract. And we can access these values from the contract instance by making multiple function calls. Once all of these state variables have been retrieved, we will just print them out to the console. And following that, we do need to perform some kind of processing of the deadline date. The deadline for the crowdfunding campaign will be displayed to any user who accesses the fundraising web page, and we do need to convert it to a human readable format. Note here that we are also creating a variable called deadline, which is meant to convey whether the fundraising campaign has finished or not. If the deadline has passed, then the fundraising campaign has finished, and if not, then the campaign is still ongoing, which is why this is the inverse of the before deadline variable. Next, we get access to each of the Ethereum accounts which are available using the drizzle.web3.eth.getAccounts method. Since the web page will be accessible on a browser, this will in fact be making a call to Metamask, and all of the accounts which are available through the Metamask plugin will be made available to this application. We then go on to access the first of these accounts which are returned from Metamask, that is the account at index 0, and we check whether this account corresponds to the account of the beneficiary of the fundraising campaign. This is because the web page will offer a slightly different view for the beneficiary, since we would like them to collect the campaign funds in the case of a successful fundraising campaign. So once we have all of this information, we will populate the state variables which we had defined previously, calling the this.setState method. So we're populating all of the fields within the campaign object. We now move along to the definition of the render function for the campaign component. And again, we will first check whether the Drizzle component is still loading. And once the loading is complete, we will create a variable called state, which effectively has access to all of the state variables defined within the campaign component. Many of those state variables will be displayed to the user, and some of the others will be used in order to perform some logical checks to determine what actions are available for the user. One field which determines what actions are possible is the state of the campaign. Here, we access the campaign state and load it into a variable called status, and it is after this where we begin the definition of what will be displayed on the web page. So here we are returning a div tab which includes a table, and this table will display a number of name and value pairs, which is why we set the column headers for the table right here, which are name and value. The name will convey the name of some field of our campaign related data, while the value column will represent its corresponding value. Moving along now from the header of the table to the body, we start off by displaying the name of the contract or the name of the fundraising campaign, and the value which we display here is accessed from the variable state, which we initialized at the beginning of this render function, which of course maps to the state variables of this campaign component. The next piece of information we display is the target amount, and then the next row includes the total collected by the campaign so far. And this is followed by whether the campaign is currently running or has finished. We also display what the deadline for the fundraising campaign is, and will also show whether the current user happens to be the beneficiary of the fundraising campaign. The last bit of information displayed in the table is the contract state, and at the footer of the table, we make a call to the function called Campaign Interaction Section. This is where we will present a button which will allow the user to interact with the fundraising campaign, either by making a contribution or by finishing the campaign, or in the case of the beneficiary, by collecting the funds raised by the campaign in case of a successful operation. So this concludes our render function right here, and we will just close down the table definition and also the div tag. So the information which will be displayed on this web page for the campaign includes all of the details which we have populated in this table, such as the name of the campaign, the total amount of funds collected so far, the current state, and so on. And right at the bottom of the page will be a button which will allow the user to interact with the campaign. And the specific nature of this interaction is determined by the current state of the campaign and also by the user who is connected to the page. We will define these interactions in the next video. In the previous video, we started coding up the campaign component of the front end of our decentralized application. So this is the fundraising campaign details which will be published within that campaign component. And we made available to the user a table displaying various details of the campaign. And at the footer of the table, we made a call to this function, Campaign Interaction Section. Through this function, we will determine what kind of interaction is possible for the user depending on the current state of the campaign and also who the user is. So when we take a look at this campaign interaction section function, we see that we first check what the state of the campaign is. If the campaign has finished, which means that the deadline has passed, then we call the function post-campaign interface. And if the fundraising deadline is still in the future, then we call the contribute interface function. We now move along to each of these functions here. So if the deadline has passed, then the post-campaign interface function will be called, where we first perform a check to see whether the campaign state is ongoing. If so, we will return a button which will allow the user to finish the campaign. So by clicking the button, the user will trigger a function called onFinish, which we will define just a little later within this JS file. So finishing the campaign is one of the possible interactions for the user, which takes us along to the second interaction, where we perform a check for two conditions. Firstly, we check whether the fundraising campaign is in the succeeded state, where the required funds have been raised before the deadline, and also if the user who is currently connected to the web page happens to be the beneficiary. If both these conditions are met, then the beneficiary will be presented with a button in order to collect the funds which have been raised in the campaign. And this button will trigger the onCollect function, which we will define just a little later. So while this defines an operation for a successful campaign, we move along now to a failed campaign, where the campaign state is failed, and this is because the target amount has not been raised before the deadline. In such a case, we will present the user with a button to trigger a refund operation. The implementation of this refund operation is in a function called onRefund, and that once again is available just a little further down in the source file. So these three operations which we have defined so far complete the post-campaign interactions which are possible. We now move along to the situation where the campaign is still ongoing, in which case an individual will be able to make contributions towards the campaign. In this case, the user is presented with an input field where they can specify their contribution amount to the campaign. And then they will also have a button which they can click, which will trigger the onContribute function. Once again, we will just define that a little later. Once a user has made a contribution, we will update the state variable contribution amount so that it can be accessed by the onContribute function. The contribution amount needs to be specified in the units of Ether. So now that we have defined at a high level the different interactions with the fundraising campaign, we now implement each of the functions which are needed for those interactions. Starting with the onContribute function. So here we get access to the Drizzle instance, and then we retrieve all of the users' accounts which are accessible through Metamask. This is by the call to drizzle.web3.eth.getAccounts. And then we retrieve the contribution made by the user, which we had loaded into the state variable contribution amount. And note that we are converting this amount specified in Ether to the units of Wei. So we now have the amount of Ether contributed by the user along with all of their Metamask accounts, and we will use that information in order to trigger a transaction. Specifically, we will access a contract instance and then trigger a call to the contribute method defined within it. And since this is a payable function, we not only need to specify an account which is used to trigger this transaction, but we also specify a value which is the total amount of Wei being passed along to the contract. So the first account from the Metamask account list will be used to trigger this transaction, and the value being passed to the contract is the contribution amount specified by the user. So once a call to the contribute function is triggered, the total amount of funds collected by the campaign will have changed. So we will update the value of the field campaign.total collected to reflect the latest contribution made by the user. So we will update the state variable by making a call to this.setState. Next, we move ahead to the definition of the onFinish function, and this is something which can be invoked once the deadline for the fundraising has passed and the state of the campaign is still ongoing. Here we get access to the Drizzle instance and retrieve all of the user's accounts from Metamask. And then using the smart contract instance, we trigger a call to the method finish crowdfunding. This will have updated the state of the fundraising campaign. So we retrieve the latest state and then update our own local state variable right here. In the case of a failed campaign, a user can invoke the onRefund function. And in this case, once we retrieve the Drizzle instance, the accounts, and the contract instance, we make a call to the withdraw function defined within our contract. Once again, this transaction is triggered by making use of the first account returned from Metamask. The last function which we define in this code is the onCollect function, and this of course can only be triggered by the beneficiary of the fundraiser after a successful campaign. So here, we will trigger a call to the collect function within our smart contract, and the parameters for the function are similar to what we have used previously. And with that, all of the different functions as well as the data to display for our campaign component have been completed. At the very end of this source file, we will export the campaign module so that it is available for any other source files which import it. And very importantly, we will need to save down the source file as campaign.js. So with that done, we have defined our app component, which is the top level component of our web application. There we set up a subscription to our deployed fundraising smart contract, and then we passed it along to the only subcomponent, which is this campaign component. Within our campaign component, we display some information related to the fundraiser to the user, and we also present to them different options for interacting with the fundraiser. Users will be able to contribute towards the fundraiser in case the state is still ongoing, and in the case of the deadline having passed, they will be presented with a number of other interactions. At this point, all of the coding work for our front-end application is complete. All that remains is for us to bring up the web UI and then interact with our application. So far in this course, we have completed the coding part of the front-end application for our dApp. We can now go ahead and close all of these files which we have coded up. So just closing down campaign.js, app.js, and the index.js file. And we can head over to our shell and note here that I'm in the source directory within the client application. And from here, in order to start up our React application, we just need to run npm start. So this will bring up our React app and it will be accessible from a web browser. So we can just wait for this loading to complete. And once our app is ready, we will be presented with the URL from which it is accessible. So I'm now just going to copy over this localhost port 3000 URL, and you will have something similar show up in your case. And we can bring up our web browser. So I'm now going to navigate to this URL, and we can see this loading Drizzle message coming up because the component is still loading. And if you observe the Metamask icon in the top right, there is a notification which has appeared. In my case, this has come up on a different screen, so I'm now just going to drag it here. And we are notified that our application is requesting access to our account on Metamask. This is exactly how Metamask is supposed to work, where it injects a Web3 object into any page which is loaded in the browser. And if your application happens to be Ethereum enabled, it is looking for that Web3 object and will use that in order to connect to Metamask. Metamask in turn is now currently connected to our private Ethereum network, and this is how our application will be able to interact with our smart contract deployed to that network. Now I'm going to confirm here that this crowdfunding application should be able to connect to Metamask. And with that done, the home page of our application is now visible. Note the hierarchy of components which we had specified in our application. The title for this web page, which is crowdfunding application, where crowdfunding is a single word, appears in the top left, and this was set in the index.html file. Within our app.js file, we specified a header for crowdfunding application where crowdfunding is 2 words, and that appears in the body of the page. And then the table which contains all of the details of this crowdfunding campaign was defined in our campaign component. So we can see here that the deadline for this crowdfunding campaign in my case is 7:02 a.m. and it's currently 6:49 a.m. for me. So I'm still well within the deadline for the crowdfunding campaign. But in your case, if your deadline has passed, then you can redeploy the smart contract using Truffle Migrate. And this should include new build artifacts, including the JSON for the contract. Since there is a symbolic link from your client app's source directory over to the build artifacts, it will automatically pick up the latest version of the deployed contract. And the crowdfunding deadline should be in the future. Once you're ready, you can go through the different fields which are visible here, including whether you are currently signed into Metamask as the beneficiary. So my current active account in Metamask is not the same as the beneficiary account, which is why I see false here. So I'm now going to head over to Metamask. So this is currently account number 1, which has been used previously to deploy the contract. And I'm going to make a switch to account number 4. And this was the one I had set as the beneficiary in the deployment script for the crowdfunding smart contract. So make sure you follow my lead and switch over to the account which you had set as the beneficiary. And once that is done, you can see the Ether balance right here. And with the switch made, in order to view the page as the beneficiary would see it, we will need to perform a refresh. This will ensure that Metamask injects a new Web3 object into the web page, which in turn will update the active account which is currently available to our campaign component. And with that done, we can see that this beneficiary field reflects that we are currently signed in as the beneficiary account. You will also observe from the availability of the contribute button that the beneficiary is capable of contributing to their own campaigns. But in order to make these contributions, we will switch over accounts in Metamask. So I'm now going to bring it up and then switch back to account number 1. At this point, let us make a quick note of the Ether balance in the account which we are using for this contribute transaction. And for me, this is about 96.7 Ether. So once that is made, I will refresh the page once more so that the details displayed on the page will reflect the fact that I'm not a beneficiary now, and that account number 1 for me will be used in order to invoke any transactions. So let us go ahead and create such a transaction where we will now trigger a contribution of 10 Ether towards this fundraising campaign. Note here that the state of the campaign is still ongoing, and also the target fundraising amount is 40 Ether. But before we hit the contribute button, let us take a quick look at the status of our Ganache network. So bringing up the Ganache UI and then heading over to the Transactions tab, we can take a look at the latest transactions which have been recorded, which in my case is an operation on the migrations contract. And we can also take a look at the latest block which is active in the blockchain, which in my case is number 38. Heading over to the Contracts tab, we can view the different contracts which are available here. And then heading over to Events, the latest events can also be taken a note of, because all of these are likely to change once we begin interacting with our contract from our front-end application. Heading back now to our web application, we will go ahead and make this contribution of 10 Ether towards this fundraising campaign. So we can just go ahead and hit the contribute button, and immediately a couple of things have changed which we can make a note of. Firstly, the total fundraising amount collected has been changed to reflect the fact that we have contributed 10 Ether. And this is an effect of us updating the state variables in our campaign component in the onContribute function which we define in our campaign.js file. This contribute transaction, however, is not quite complete yet, and you will notice that there is a notification which has come up on Metamask. And I'm going to drag that notification over to the screen now. And we will need to confirm that we wish to proceed with this contribute transaction, which will transfer over 10 Ether to our smart contract. So this is how Metamask serves as a go-between between the front end and back end of our decentralized applications. In addition to the 10 Ether being transferred over to the contract, there is also a small gas fee which we'll need to pay out. And this is something which is configurable within Metamask. We will not do that, however, and just go ahead and confirm this transaction. And with that done, we can bring up Metamask, where we get this confirmation that 10 Ether has been deducted from this account since the balance has dropped from about 96.7 to 86.7. The balance has actually dropped by a little more than 10 Ether because we also paid a gas fee. The details of the transaction are visible right here. So this was a contract interaction which deducted 10 Ether from our accounts. And this transaction has also been confirmed. And when we expand this, the full details of the transaction will be visible. So now that we have invoked our first transaction from the front end of our application, in the next video, we will take a look at what effect that has had on the Ethereum network by bringing up Ganache. In the previous video, we brought up the front end of our crowdsourced fundraising decentralized application. We also submitted a transaction where we made a contribution towards the fundraiser of 10 Ether, and we got the confirmation that the transaction has gone through and has been recorded on the blockchain. It is now time for us to view the effects of that transaction on our blockchain network, for which I'm going to bring up the Ganache UI. From the current block number, it was previously 38 in my case and is now 39. So a new block has been added to the blockchain. I'm currently in the Events tab, and all I see are 3 encoded events because the details have not been refreshed yet. To do that, I'm now going to switch over to the Contracts tab, where we haven't really deployed any new contracts, so no new information is visible here. And then switching back to the Events tab, the top event here reflects the fact that a contribution has been made to the contract. We can even see from the block time that this is in fact the latest contribution which we have just made. We can click on this event in order to view additional details for it. And here we still see this notification that we need to link a Truffle project in order to view rich event data. But if we further click on this event here, we do in fact see more information. We can see exactly which smart contract this particular event is linked to, which of course is our crowdfunding with deadline contract. We can also view the signature of this event. And then finally, all of the details for the event, which includes the contract address, also the contribution amount, which is stated in way, and the state of our fundraising contract, which is ongoing, are all visible here. So this is how we can view the details of the events which are emitted by our application from the Ganache UI. From here, we can head back to the main events page and then head over to accounts, where we will observe once more that the Ether balance of this account which was used to make the contribution has dropped by about 10. Heading over now to the blocks. Block number 39 is the one which contains our latest transaction. And to view that transaction, we head over to the transactions view, and the details of this transaction are available in the top. We can also see that the value of Ether transferred in this transaction was 10. Heading over now to the contracts tab, we can scroll down to one of these instances of the crowdfunding with deadline contract to ensure that the 10 Ether which was contributed is now available in the contract account. So when we click on this, we have that confirmation. The Ether balance for this contract account is now 10. We can also view the values of the different fields in our smart contract. And then heading over to the transaction section, our latest transaction has successfully been linked to this smart contract. Even the latest contribution event is now available in this view. So we have now seen, using Ganache, the effects of our contribute transaction on the blockchain network. At this point, we can head back to our application. So I brought up the web app now. And then we will make another contribution towards this fundraiser, for which we will sign in as a different account in Metamask. So bringing up Metamask now, I'm going to switch over to account number 2. And this currently has an Ether balance of 101. Again, make sure you refresh the page for this current account to become the active one. The contribution made by this account is going to be 20 Ether in all. And we'll just go ahead and hit the contribute button. And immediately the total collected field in the table here has been updated from 10 to 30. However, the transaction has not yet gone through, so I'll just go ahead and bring up the MetaMask notification. And we'll go ahead and confirm this transaction for 20 Ether. Now, to ensure that the transaction went through successfully, we can bring up MetaMask. And we observe two details here. Firstly, this contract interaction transaction has been recorded and 20 Ether has been deducted. And the Ether balance for this account also reflects that 20 Ether has made its way out of this account. Now we can expand this to view the details of the transaction, but more details will be available in the Ganache UI. So I'm now in the Events tab, where another contribution event has appeared here. We can now move over to the Accounts tab, where first of all, we can confirm that the current block is now 40 in my case, and the Ether balance of this first account is still the same, but that of the second account has dropped by 20. Heading over to the blocks, we can see block number 40 here. And then to transactions, our latest contribution transaction has also been recorded. Heading over to contracts, we can check out this instance of our own smart contract. And we can confirm that the Ether balance for this contract is now 30. We can view the state variables as well. And then heading over to the transaction section, there are now 2 of these. And then there are also 2 events which have been recorded. So we can just head back from this events view and then back to our web UI, where we currently see that we are 10 short of the fundraising target amount. So let us go ahead and fix that so that this fundraising campaign is a success. So I'm now bringing up Metamask and we'll switch over from account 2 in my list over to account 3. So this has an Ether balance of 100 right now. And before we make any contribution from this account, we do need to refresh our web page so that our newly selected account becomes the active one, and then make this contribution of 10 Ether. So just hit the contribute button, which of course will bring up a Metamask notification, but it also updates the total collected field here to 40, which matches the target amount. But just to see this transaction through, I'll bring up the Metamask notification and hit confirm. And to ensure that the transaction went through, we'll bring up Metamask once more, where we can view the record of our newly invoked transaction. And we can also see that the balance of this account has dropped by 10. So this fundraising target has been reached before the deadline has expired. In the next video, we will go through the remaining steps in order to mark the campaign a success and for the beneficiary to collect the funds which have been raised. So far in our interactions with our front-end applications, we have made multiple contributions towards this fundraising campaign, and the fundraising target of 40 Ether has been met, and this has been met before the deadline in my case. So for me, the expiration of this fundraising contract is 7:02 a.m. and it's still currently 6:54 a.m. for me. Now you will recall, if you take a look at the contribute function in your smart contract, there are a couple of checks which are performed. First of all, we ensure that the deadline has not yet passed, and only if it hasn't do the contributions actually take effect. And then following that, we perform a check to see whether that particular contribution has tipped the amount of funds collected above the fundraising threshold. If so, we set this collected variable in our smart contract to true. And that is the variable which determines whether the fundraising was a success. To summarize, as long as the required contributions come in before the fundraising deadline, then the fundraising is considered a success. So now, even if I were to wait a few minutes for the deadline to pass, so I'm just going to fast forward here until the deadline of 7:02 has been exceeded. So at this point, even though the deadline has passed, it is still possible for the beneficiary to collect the funds raised, since everything is still in place to mark this fundraising a success. To do that, however, we will need to explicitly finish the campaign. So I'm now going to head back to the web app and refresh the page. And you will notice that this has finished value now shows up as true. And also the button to finish the campaign is now available. So any user of this application has the ability to mark a campaign as finished. And you don't necessarily need to be the beneficiary. The collection of the funds, however, can only be done by the beneficiary account. You will notice though that the contract state is still ongoing because we have coded up our application in such a way that we need to explicitly mark the campaign as finished by executing this finish campaign function. So that function will be triggered when we hit the button. So let us go ahead and do that. And now a Metamask notification should pop up. So I'll just drag it over to the screen and then hit confirm. There is no Ether which is making its way to the contract account here. And we can confirm that by bringing up Metamask, where the Ether balance for this account is pretty much unchanged since there was only some gas fee which was paid out. And this contract interaction transaction confirms that no Ether was transferred over. All right, so we can go ahead and refresh this page to see whether the state of the contract has changed since we ran the finish campaign function. And yes, Now the campaign has been marked as a success. You will also observe that there is no button visible right now because we had coded up our application in such a way where a user who is not the beneficiary will not be able to perform any interactions with the contract once it is marked a success. So the only interaction possible at this point is for the beneficiary to collect the funds which have been gathered into the contract account. Now, before we connect as the beneficiary, we can take a look at the transaction and the events which have been emitted from the Ganache UI. So I'm currently in the Events tab, and this is still showing the contribution event as the latest one recorded, and we will need to refresh this. So from the Events tab, I'm just going to switch over to one of the others, such as the Contracts tab. And there are no new contracts here, of course, so I'm just going to switch back to Events again. And at the very top, this campaign finished event has been recorded here. We can click on it in order to view its details. Once again, the name of the contract appears here, along with the signature of the event. And we can also view in the return values the contract account address and also the total amount of Ether which has been collected into the account, though the value of the succeeded variable is not visible. Moving along now to the Contracts tab, we will head over to our Crowdfunding with Deadline smart contract here, which now has a total of 4 transactions linked to it. And we can confirm that the balance of Ether in this contract account is 40. From the state variables, we can see that the collected variable is true and that the state is succeeded. And scrolling further down, we can see the details of the latest transaction and also the latest event recorded with this contract. So at this stage, the last thing for us to do in order to complete this successful fundraising campaign is for the beneficiary to be able to collect the funds raised and then transfer it over to their own accounts. To do that, we can head back to our web application, and then from Metamask, we will now switch over to the beneficiary account. So in my case, this is account number 4 from Metamask. So I'll just make that selection. And the balance in this account is currently 100 Ether. So we expect that this account will have about 140 Ether once everything has been completed. So we will need to refresh the web page in order for the beneficiary account to be picked up. And when that happens, we will see that this I am beneficiary field is now showing up as true. And also, unlike the regular user, the beneficiary is able to see this button in order to collect the funds which have accumulated into this contract. And the logic which we had coded up was this button will only be available if the campaign has been marked as finished. So let us go ahead and allow the beneficiary to collect the funds which have been raised by this campaign. So we hit the Collect Funds button, and this, of course, will bring up a MetaMask notification, which I'll just drag to the screen, and then hit Confirm. When we do that, we will need to wait a little bit, and then bring up MetaMask once again, just to confirm that the transaction has gone through. And yes, we can see, first of all, that the Ether balance of this account has gone up from 100 to nearly 140. And there is also a record of our most recently invoked transaction right here. So this was a call to the collect function. And we can also confirm that by heading over to the Ganache UI, where I will head over to the Events tab. And the latest event to be noted here is the one for collection. We can just click on it in order to view the details. So we have the contract name, the signature, and most importantly, the fact that the total collection amount was 40 Ether, and the string which we had passed when emitting this event was succeeded state. So the logic of our application seems to work exactly as we planned it to. We have now performed all of the steps in a successful fundraising operation. However, there is one detail which we still need to check out. Once the collection of the funds has taken place, the state of the contract should be paid out, and we need to ensure that this is in fact the state which is reflected in our front-end application. So I'll just head back to the browser now, And just in case your page hasn't automatically refreshed, you can just go ahead and explicitly do that. And the state of the contract has now been updated to paid out. You'll also note that even though we are currently connected as the beneficiary, there are no further contract interactions which are possible. And this will also be the case if you connect as some other user. So this crowdfunding campaign was a success. We can now do a full sanity check by simulating another fundraising campaign which does not raise the required funds before the deadline. So far, after having successfully built up the front end of our decentralized application, we have played out the scenario where there is a successful fundraising campaign where we made multiple contributions towards the campaign from several accounts, and then we were able to mark the campaign as finished and for the beneficiary to collect the funds which the campaign had raised. It is now time for us to test out the other scenario where the campaign is a failure and the deadline has passed and not enough funds have been accumulated. For that to happen, we will now need to deploy a new instance of our smart contract. So I have now brought up the text editor, which includes the entire Truffle project directory. And from the build directory, which contains all of the build artifacts, we can head over to the contracts subdirectory. And this includes the 4 JSON files for each of the 4 contracts which this project currently has. Very importantly, this includes our crowdfunding with deadline smart contract. Now, in order for us to deploy a new instance of our contract, I'm just going to go ahead and delete the entire build folder. Since we don't need any of those artifacts now, we can just get rid of that. So I'll just delete this. And before redeploying the contract, I'm going to make a minor change to one of the deployment scripts. So heading over to migrations and then to the third deployment script, which is the one where we deploy and then initialize our crowdfunding with deadline smart contract. So when we bring this up, the change I'm going to make is to the deadline for the contract. So previously it was set to 30 minutes. And now I'm going to let it expire within 10 minutes so that we don't really need to wait as long as we did previously for the deadline to pass. All of the other parameters remain exactly the same, including the name of the campaign, the amount of funds to raise, which is 40 Ether, and also the beneficiary address, which again for me is account number 4 in Metamask. With this change made, we can just save the changes to our deployment script and then close it down. And at this point, in order to redeploy our contracts, we head back to the shell, where we will need to run the deployment scripts once more. But to do that, we need to be in the root directory of our Truffle project. So I'm now just going to head over to the root crowdfunding directory. And from there, we will once again run the Truffle Migrate command. This migration will take place to the Ganache network as defined in our Truffle config file. But we also explicitly specify the reset option so that all of the migrations will run from the beginning. And when we run this, we will see that the Truffle compile runs once more. And we also see that all of the migrations do occur from the beginning, including the migrations contract and also our utils library, and most importantly, our crowdfunding with deadline contract. Heading back now to the text editor, this build directory has reappeared, and this contract subdirectory also exists within that. And in that directory, all 4 of these JSON files have been regenerated. Now, do we really need to do anything about our front-end application so that it picks up these changes? Well, the answer is no, since we already have a symbolic link to this build/contracts directory, and the app will just pick up the latest JSON files rather than the previous ones. To confirm that though, we head back to the shell, and just to ensure that we start off with a clean slate, you can close down the previous web application in case it's still running. And then from here, we will cd into the client/source directory. And then we will restart our web app by executing npm start. So within a few seconds, we will once again have this web app which will run on port 3000 of our local host. So I'll just bring it up in the browser now, and we'll just refresh this page which was up previously. And when we do that, our new version of the crowdfunding application is now visible. The target amount is still 4 Ether, but the total collected is a grand zero. And very importantly, the new deadline, at least in my case, is 7:24 a.m., which is just a little under 10 minutes away. So in order to begin transacting with this application, I'm going to switch the account. So I'm currently connected as the beneficiary account here. So I'll bring up Metamask and then switch to one of the other accounts. Let's just say account number 1. So this has an Ether balance of a little over 86 Ether. So with the selection made, I'll just hit refresh once again, and the page has been reloaded and it confirms that I'm not the beneficiary now. So I'll just go ahead and make a contribution from this account. So once again, we'll contribute 10 Ether, and the total collected field has quickly updated. But the transaction has not yet gone through, so I'll bring up the notification from Metamask here and hit confirm. Heading over now to Metamask again, the Ether balance is now 76 Ether, or rather a little over that, and the latest contribution transaction has also been recorded. We can also quickly confirm that the Ether has made it to the contract. So I'm just going to bring up Ganache for that, and then head over to the Contracts tab. From here, I'll just navigate down to this latest version of the crowdfunding with deadline smart contract, and clicking on it confirms that the Ether balance in this contract is now 10. We can also scroll down to view that there is just one transaction associated with this contract, and there is also a contribution event which has been emitted. We can just head back to our web UI now, and then bring up Metamask once more, and we will perform a switch to one of the other accounts. So this time is going to be account number 2, and this currently has an Ether balance of just about 81 Ether, and we'll also go ahead and refresh the page. We can now make another contribution towards this fundraising campaign. So as account number 2, I will once again make a 10 Ether contribution, and after hitting the contribute button, the total collected field has now updated to 20 Ether, but for the transaction to go through, I'll just confirm it on Metamask. Once that is done, and we see that the Ether balance has dropped by 10, and this transaction has been recorded, we can quickly confirm the Ether balance in the contract account by heading over to Ganache and refreshing this page. So yes, there is now a total of 20 Ether in this account. Scrolling further down, there are also 2 transactions and 2 contribution events. Alright, so at this stage, we shouldn't really make any more contributions to ensure that this campaign is a failure. So I'll now just head over to the main events tab here, and then switch over to accounts, where we can keep note of the Ether balances in each of the accounts of the contributors here. So accounts 1 and 2 have balances of 76 and 71 Ether respectively. And then heading over back to our application, the deadline in my case is 7:24, and there are still 5 minutes remaining for me. So I'm just going to run down the clock now, and then wait until the deadline has passed. In the next video, we will just take a look at what exactly happens in the case of a failed campaign such as this one. In the previous video, we redeployed our crowdfunding with deadline smart contract, and then we also reloaded our application to point to that new contract. We then made a couple of contributions, but ensured that the fundraising amount was not exceeded, and we also ran down the clock so that the fundraising deadline has passed. It is now time for us to ensure that the beneficiary is not able to collect the funds which have been raised, and very importantly, that the original contributors towards the campaign are able to collect their refunds. To do this, we head back to our web browser where the app is still up. And I'm just going to switch over from the account which I was using previously over to one of the other accounts. Let's just say account number 3, which has not yet made any contribution towards the campaign. Once that is done, I'll just refresh the page and you will observe that the Finish Campaign button now appears, which means that our app has detected that the deadline has passed. And this is also reflected in the value of the has finished field in our table. Now the contract state is still ongoing, however, so we will need to explicitly finish the campaign by hitting the button. And then we will confirm the Metamask notification. And then following that, we can confirm that this contract interaction did in fact go through. Now to confirm that this transaction has changed the state of the contract, we can head back to Ganache and over to the Contracts tab, access our deployed smart contract once more, and in the storage section where the state variables are accessible, we can confirm that the state is now failed. We can view each of the transactions below and also all of the events, including the one which marked the campaign as finished. And when we click on that, we can see from the return values that only a total of 20 Ether has been raised by the campaign. Now to test out the remaining scenarios, we head back to our web browser. And now I'm going to switch over my Metamask account. So I'll just switch over from account number 3 over to account number 2. As always, the page will need to be refreshed after an account switch. But when that is done, we can see over here that the refund button appears at the bottom, and also the failed state of the contract is visible in the bottom row of the table. So I had made a contribution as account number 2 previously, so this account can claim a refund legitimately. However, let us try the other option where account number 3 tries to force a refund. So I'm just going to switch over accounts once more in Metamask. Once account 3 has been selected, we'll refresh the page. Of course, the refund button now appears, but I will just go ahead and hit this button in order to trigger the refund. Since this will invoke a transaction, this Metamask notification will need to be confirmed, and immediately an error has been thrown. In fact, this error message conveys that nothing was contributed, and this is the message which we had set in the require clause in our withdraw function in the contract. So our logic has been set up correctly, where someone who has not made a contribution towards a fundraising venture will not be able to claim a refund. We will now test out a legitimate refund. So I'm now going to switch from account 3 to account 2. So this currently has an Ether balance of just a shade under 71 Ether. So I'll just refresh the page for the new account to be picked up. And we'll then go ahead and hit the refund button. So claiming this refund will still incur a gas fee, but since it's still a fraction of the refund amount, this account will still claim it. And to confirm that the Ether balance has gone up from 71 Ether, we will bring up Metamask. And yes, this account now has a total of 81 Ether, which means that 10 Ether has been successfully refunded to this account. There is still one more account which can legitimately claim a refund. So we will now switch over to account number 1, which currently has about 76.6 Ether. And will then refresh the page after the selection. Once again, the refund button is available, and we will just go and click that. And then we will confirm the Metamask transaction notification. And to confirm that 10 Ether has been credited, we bring up Metamask again. And 86.6 Ether is the new Ether balance. So both of these withdraw transactions have successfully refunded 10 Ether to the 2 accounts which made contributions towards this fundraising campaign. We can now go and check the blockchain network. So we bring up Ganache for that. And wherever you are, we can just head over to the Accounts tab, where the Ether balances of these two accounts can be confirmed. Heading over now to the Blocks tab, there are now a total of 55 blocks in this blockchain. Switching over to Transactions, we can view the details of the latest withdrawal transactions which we have invoked. But for now, we will just switch over to the Contracts tab. And from here, we can access each of the contracts, where the details of the transactions and the events will be available. But in order to view the details of our withdrawals, we can switch over to the Events tab. At the very top, we can see that there are two withdrawn events which confirm that these withdrawals have been recorded on the blockchain network. So we have performed a thorough test of our application, but there is one more interaction which we need to confirm. So I'm currently connected as account 1, and just to make sure, I'll refresh the page, and this account has already claimed their refund successfully. However, let us just say that this account forgot that they have already collected their refund and then tries to invoke this refund operation once more. They will need to confirm this Metamask notification, and this throws an error. If you examine the withdraw function in our smart contract, you will observe that when a withdrawal is triggered, we zero out the contribution which is recorded on the contract for that account, which means that when they invoke the function again, the require clause will fail and this error will be thrown. So we can just exit from this message, and what we are left with are the details of the crowdfunding campaign. So even though the Ether balance in the contract account will be 0 after each of the contributors has claimed their refund, we still have a record that the total funds collected by this particular campaign was 20 Ether, as opposed to the target amount of 40 Ether. We can also see when the deadline was, and also that the current contract state is failed, and these details can be kept as a record of this particular campaign. In this exercise, you will first write some code in order to retrieve a list of accounts from Metamask using a Drizzle instance. In order to invoke transactions from your Ethereum-enabled web application, it often helps to make use of Metamask in order to establish the connection to the blockchain network and also to supply a wallet of accounts which can be used to invoke those transactions. Now, within the code of your front end, however, you will need to define a way in which to retrieve the accounts from Metamask and then access one of the accounts from which to trigger your transactions. You'll just need to recollect exactly what those lines of code are. Next, you will invoke functions in your smart contract using a Drizzle instance. We have seen during this course that the Drizzle instance allows you to access your smart contract, and you can access the different fields in your contract state and also call the functions which are defined in your contract. These functions can either be read-only or ones which trigger a transaction, and there are different methods which you can use in order to call them. You will need to make the specific function calls in order to trigger these calls. And finally, you'll describe how an Ethereum-enabled web application connects to a blockchain network via Metamask. We saw repeatedly during this course that in order for our web front-end to connect to a smart contract which is deployed to a blockchain network, it is easier to go via Metamask. But we also saw that each time we switched the accounts in Metamask, we needed to refresh the page. You will need to recollect exactly why we need to do this, which will point you to the mechanism which is used by Metamask in order to connect the front end to your back end in an Ethereum app. Each of these topics were covered during this course, so please pause this video and then take some time to perform each of these tasks on your own. For the first task in this exercise, you needed to recollect how you can make use of a Drizzle instance in order to retrieve a list of Ethereum accounts which are linked to your Metamask plugin. Well, in order to retrieve the list of accounts, you can make use of the function call drizzle.web3.eth.getAccounts. When you make this call in your JavaScript frontend, the Ethereum accounts which have been imported into Metamask will be available for your frontend. And in order to access a specific account from that list, you can just treat this list as an array and then access the specific account using an index. In the demos of this course, since we had multiple accounts linked to Metamask and we were switching constantly between them, we always made use of the first account from this list. Also note that the Web3 object which is injected into the web page by Metamask is accessible to the Drizzle instance as drizzle.web3. For the next task in the exercise, you needed to call functions defined within your deployed smart contract from your front-end application using a Drizzle instance. Well, once you initialize your Drizzle instance using your deployed contract JSON and also the Drizzle store, it is possible for you to use that Drizzle instance in order to read from a contract by calling one of its read-only functions. And we also covered that there are read-only getter functions which are available to read the value of the fields in your contract. So consider that you have a contract called myContract and a method called methodName. A function call can be made by drizzle.contracts.mycontract.methods.methodName.call. So this is what you do in order to make a call to a read-only function. However, if your function happens to change the state of the contract or write to the blockchain, then you will need to invoke a transaction, and you can use a similar syntax to do exactly that. So if the name of the function which invokes the transaction is txMethod, then the call you need to make is drizzle.contracts.mycontract.methods.txMethod.send. In addition to the function arguments, the arguments to send include the account from which the transaction needs to originate, and if you're passing along ether to the function, then the ether value is also attached. For the final task in the exercise, you needed to describe the exact steps involved, which allows your front-end application to connect to your smart contract deployed to an Ethereum network via Metamask. So Metamask, in this case, serves as an intermediary between your application and the Ethereum network. So in order to set up Metamask to connect to a specific Ethereum network, you will need to set this up in the plugin. And the way to do that is to make use of the RPC endpoint URL of the Ethereum network. During the labs of this course, this is precisely what we had done in order to connect Metamask to our network on Ganache. Once you do that, however, only one of the accounts from your Ganache network will be automatically imported into Metamask. And if you want multiple accounts to be accessible in the plugin, then you will need to import them one by one. So this completes one end of the connection between your front end and your back end. Given that Metamask has been connected to the back end now, it will use a specific mechanism in order to allow front end applications to connect to that network. Specifically, Metamask will inject a Web3 object into every page which is loaded in your web browser. It is this object which includes the interfaces in order to connect to your blockchain network, and any front-end application which wishes to connect to that network can access this Web3 object and make use of the interfaces to connect to the backend. One more detail which is available from this Web3 object are all of the Ethereum accounts which have been imported into the Metamask plugin. It is the Ethereum-enabled applications which will use this Web3 object though, and this is what is used in order to connect the front end to the back end. And although the Web3 object is available to every single page which you load into your browser, it is only the Ethereum-enabled applications which will use it, while the others will simply ignore it. In this demo, we will define our own Ethereum token which complies with the ERC20 token standard set by Ethereum. Such tokens can be used in your own Ethereum-enabled blockchain applications and can also be issued to the general public through an initial coin offering. In this course, however, we will focus on how to set up such a token and the different operations which need to be implemented in order for a token to comply with the ERC20 standard. We will be making use of the Remix IDE in order to develop and then deploy and test out our ERC20 token. And I'm currently logged into the remix.ethereum.org website, where the IDE is accessible on the cloud. If you have used the Remix IDE previously, you may see this notification that a new UI is currently available. So you can just hit OK, and then this button in the top right in order to switch over to the new Remix interface. That is what I will be using now. So I'll just click on this and then confirm that I want to reload the page. And then following that, you may need to hit this File Explorer button in order to view the source files in a left panel. But once you're ready, you can go ahead and create a new source file by hitting this plus button. Now, before we define our ERC20 token, we will define a utilities library which the token definition can use. So this is going to be in a source file called utils.sol. And if you cannot view the source file in the File Explorer, you can just expand this browser tab and you will see the utils.sol file right there. I also have a hello world file from a previous exercise, but I'll just ignore that for now. And clicking on utils.sol, I will go ahead and paste the source code and then walk you through each of the blocks one by one. We start off with the pragma directive, which ensures that a version of the Solidity compiler between 0.5.0 and something less than 0.6.0 will be used. And we begin the definition of our utils library, which includes two different functions. And these are meant to perform addition and subtraction operations on our tokens. The first of these functions is a sub function, which is meant to perform a subtraction. It takes in two arguments, a and b, and this will return a value of a minus b, but only if b happens to be less than or equal to a. So this is a pure function because it doesn't perform any read or write operations on the contract state. Moving along now to the add function, which is also a pure function and again takes in two arguments, a and b, and then returns the sum of those two numbers, provided that sum is greater than or equal to the value of a. This ensures that the value of b is not negative. So we have defined these two utility functions, and these will be used in our token definition to keep track of the token balances of different accounts, and also to keep track of the token allocations which one account may have supplied to another. We will see exactly what that means and how it is implemented in just a little bit. And that implementation will take place in a new source file, and this is going to be the main source for our ERC20 token definition. So we can just call it erc20.sol. Just as before, I'll just paste the source code and walk you through each of the blocks. We start off with a pragma directive, and then we will import our utils library into this source file. The name of this contract is going to be Looney, and you can think of this token as some form of local currency in a specific domain. Now, within this contract definition, we specify that we will be using the utils library and make sure all of its functions are available. And then following that, there are three different fields which we define within our token definition. And these are strictly optional, but they often make it more convenient to work with a token. These fields are the full name of the token, which in our case we can call Looney, and then a symbol, which is usually a shortened version of the full name. You can think of the name and symbol as being analogous to a company's name and its trading symbol on a stock exchange. The final field which we define here is called decimals, and this represents the number of decimal places which can be used to specify units of the token. In most regular currencies, this is down to 2 decimal places, but 18 is the norm for most Ethereum tokens. Now these cover some of the optional fields for an ERC20 token, and we now move along to some of the compulsory inclusions, including these 2 events. The approval event is emitted when someone triggers the approve function, and that is one of the mandatory functions for any token complying with the ERC20 standard, and it is invoked when one account grants authority to another account to spend their tokens. We will get to the actual implementation of the approve function in just a little bit, but it will emit this approval event, which will record the address of the token owner, as well as the address of the one who has been granted authority to spend tokens, and the number of tokens which they have the authority to spend. There is also a transfer event, and this is emitted by a transfer function. That function is invoked to transfer tokens from one account to another, and the transfer event records the source, the destination, and the amount of tokens transferred. Which takes us now to 2 very important mapping variables. The first of these is called balances, and it keeps track of the token balances for different accounts. That is, this mapping structure is supposed to keep track on a global level all of the accounts which possess these ERC20 tokens and what quantity of tokens they possess. There is also a mapping structure called allowed, which keeps track of how many tokens a particular account has allocated to another account to spend on its behalf. The key of this mapping structure is the address of the token owner, and the value is also a mapping structure whose key represents the account which has been allocated a certain number of tokens by the owner. The value is the total value of those tokens which have been allocated. An important property of this contract is the total supply of the tokens in circulation. In the case of our Looney token, this total supply will be initialized when we deploy the contract and cannot be modified after that. However, there may be some token implementations where the total supply of tokens in circulation can be modified under specific conditions. Now that the properties and events for this ERC20 token have been defined, we will move ahead to the constructor and all of the functions which need to be implemented, but that will happen in the next video. In the previous video, we started off defining our custom token which complies with the ERC20 standard set by Ethereum. To comply with the standard, there were 2 events which we needed to define, and those were the approval and transfer events. The fields, such as name, symbol, and decimals, which we defined, are optional, but they definitely make it easier to work with the token. And then there are the balances and allowed mapping instances, along with the total supply variable, which will be used in the mandatory functions which we need to implement for this token. We will now take a look at what those functions are and how they can be implemented for our token, and we will start off with the constructor for our token. So when this contract for our token is deployed to the Ethereum network, we will initialize it with a total supply quantity. As touched upon, this determines the total quantity of the token which will be in circulation, and the constructor is the only point at which this total supply quantity can be set. Following that, we allocate this entire initial supply to the account which has deployed the contract for the token. So we update the balances structure for this, and initially the one deploying the contract will be in possession of all of these Looney tokens. So it is up to them to distribute these tokens to other accounts following that. We now move along to the mandatory functions which we need to implement to comply with the ERC20 standard, starting with the total supply function. This needs to return a number which matches the total supply of the token which is in circulation. While you may choose to calculate this total supply quantity in many different ways, the simplest solution is the one which has been adopted right here, where we just return the value of this total supply integer variable. Moving along now to the next mandatory function, which is the balance of function. So this will take in the address of a particular Ethereum account, and it will return the quantity of the tokens which are owned by that account. In the case of our token, all we need to do is to do a lookup in the balances structure. So the key will be the name of the token owner, and the value which is returned is the quantity of the token which they possess. Now, once someone is in possession of tokens, they will be able to invoke the transfer function in order to send some quantity of tokens to another account. So the arguments to this function include the recipient as well as the number of tokens being transferred to the recipient. Now, this function can only be invoked by someone who possesses some tokens. So we first perform a check in this require clause that the balance of tokens for the one invoking this function is greater than or equal to the quantity of tokens being transferred. So this way we ensure that no one is able to transfer more tokens than they possess. So if this require clause is satisfied, then the code execution can proceed to the actual transfer of the tokens. Here we will update our balances structure by subtracting the quantity of tokens being transferred from the balance of the one invoking the transfer. At the same time, we also increment the balance of the recipient of the tokens by that same quantity. Do note here that we're making use of the add and sub functions which we defined in our utils library. Once our balances table has been updated, we will emit the transfer event, whose arguments include the addresses of the one invoking the transfer, as well as the recipient and the number of tokens being transferred. And finally, we return the Boolean value true to denote that the transfer was a success. Moving along now to the approve function, and this is a function which you can invoke in order to authorize somebody else to spend your tokens. As an example, consider that a company may authorize one of its employees to spend a certain number of tokens in order to make a purchase. The arguments to this function include the address of the one delegated to spend the tokens, along with the quantity of tokens they are authorized to spend. We will need to update the allowed mapping variable for this, where the key is the address of the account which is issuing this authorization, and then the value is another mapping instance, where the key is the address of the delegate, and the value is the number of tokens which they are authorized to spend on behalf of the approver. We also emit the approval event, which includes the addresses of the one invoking the function, the delegate, and the number of tokens. Just as with the transfer function, we return true to denote that this approval was a success. Now, if you wish to check whether someone is authorized to spend tokens on behalf of someone else, you can call the allowance function. So this is another mandatory function, and this takes in the address of the token owner as well as the address of the one delegated to spend the tokens. We will perform a lookup in our allowed table, and this will return the number of tokens which the delegate is authorized to spend on behalf of the owner. So both the approve and the allowance functions are related to the authorization of a delegate to spend tokens on behalf of somebody else. Now, in order to perform the actual spending of those authorized tokens, there is the transfer from function, which also needs to be implemented to comply with the ERC20 standard. This is a function which will be called by the delegate, and the arguments include the address of the actual owner of the tokens, the address of the recipient of the tokens, as well as the number of tokens being transferred over from the owner to the account of the recipient. Now, within the approve function, we did not perform any checks to see whether the owner is actually in possession of the tokens which they are authorizing somebody else to spend on their behalf. That does not violate the token standard, because it is only during the actual transfer operation where we perform a check to ensure that the owner is in possession of the tokens which are being transferred over to someone else. This is exactly what happens in the first require clause here, where we check that the token balance for the owner is greater than or equal to the number of tokens which are being transferred over. The second require clause is to ensure that the delegate who is invoking this transfer from function does have the authority to transfer over the specified number of tokens from the owner's account. If these two conditions are met, we will implement the actual transfer of tokens. So the token balance of the owner is decremented by num tokens, and the balance of the buyer is incremented by that same quantity. And also the quantity of tokens which the delegate is authorized to spend on behalf of the owner is also decremented in the allowed variable. Once again, make note of the use of the add and sub functions from our utils library. And finally, we will emit the transfer event once more, which includes the addresses of the owner, the recipient, and the number of tokens being transferred over. To denote a successful token transfer, we return true. And with that, our definition of this ERC20 compliant token is complete. We can now go ahead and deploy this. So the deployment of this contract and any interactions with the token will be covered in the next video. We have now successfully developed our ERC20 compliant token. It is now time for us to deploy the smart contract and then interact with it in order to test out its various features. To do this in this new version of the Remix IDE, we will need to enable a few plugins. To do that, we can click on this plugins icon in the left menu and then scroll down and look for the two plugins. The first one we will need is the one to deploy and run transactions. So we can just click the activate button next to that, and this will appear in the active modules section, and you can deactivate the plugin if you need to. We will go ahead and add the Solidity compiler plugin. So scrolling down in the inactive modules list, we'll just choose to activate this one as well. So for the purposes of this demo, these are the only two plugins which we require. So we can just go ahead and hide the plugins menu by clicking this icon once more. And then to head over to the Solidity compiler, we click on this compiler icon. Now it is possible for us to compile our source code. And to do that, we can select from the different versions of the Solidity compiler available in this drop-down menu. So there are multiple versions available, and you will be familiar with this if you have used Remix IDE before. And I'm just going to select one of the newest versions available, which is not a nightly build. So this is version 0.5.8. With that selection made, we can now build our source files. And if you're still unfamiliar with the Remix IDE, do note that there is an option to enable auto compile. However, for now, we will stick with the manual compile, and we just need to click on this compile erc20.sol button. The compiler will recognize that this particular Solidity source file does depend on the utils library, and that will be compiled as well. So we can just build our source by hitting the button. And once these buttons appear in the left menu at the bottom, it means that the compilation is successful. The green check mark next to the compiler icon in the left panel also confirms that the compile operation was a success. Now, if you'd like to view the output of the compiler and also some of the related details, you can click on the compilation details button right here. So this gives, for example, the name of the contract which has been deployed. And there is additional data such as some metadata related to the contract, as well as the bytecode. And there are several details available if you scroll further down. And right at the bottom, you can also take a look at the related opcodes. We won't be concerned with this now. But if you head over to this contract drop-down menu, you will observe that there are two contracts which are available for us to view. One of these is the Looney contract, which we just defined. And even the utils library can be accessed from here. So if you happen to be using this utils library along with some other contracts as well, then you can access the build artifacts of the library by taking a look at the compilation details. However, that is not our concern right now. And instead, we will move over to deploying our ERC20 token, for which we can click on this deploy icon in the panel on the left. From here, we have the option to deploy our contracts, and the Remix IDE provides us with a few options in terms of the environment into which we can deploy the contracts. We can, for example, deploy to our own private Ethereum network provisioned on Ganache by selecting the Web3 provider option and then supplying the RPC endpoint URL for the Ganache network. If you wish to integrate the Remix IDE with Metamask and then deploy your contracts to the network to which Metamask is connected, you can choose the injected Web3 option. But if you just want to quickly deploy and then test out your contract, the best option is to select the JavaScript VM. This will deploy the contract to a virtual environment, and this is also the one we will be selecting for this demo. Once the selection has been made, we can head over to this Accounts dropdown, and we observe that automatically 5 Ethereum accounts have been set up for us, which we can use for our own testing purposes. Just like with the Ganache network, these accounts have been loaded with 100 Ether each, and we do have the option of adding additional accounts if that is what we require. But I'm just going to select this first account here, and then following that, we can just quickly take a look at the other options available in this interface. So the details for any transaction can be supplied here, including the account from which the transaction should originate. We can also specify the gas limit, and we can also transfer Ether along with the transaction, and the units of Ether can be specified in either Wei, Gigawei, Fine, or Ether itself. We don't really need this right now because we will be working with our ERC20 token. And now, in order to deploy our token contract to the blockchain network, we can select this Looney contract from the drop-down list. This will ensure that not only is the Looney contract deployed to the network, but also its dependency, which is the utils library. We are almost ready to deploy the contract, but before that, we can take a look at this console which is available in the Remix IDE, where a lot of the log messages will appear. So now that we know what the Remix IDE looks like, we can just go ahead and deploy our contract. So we will make use of this deploy button right here, and the arguments which we need to provide to the constructor of our contract can be supplied within this text field. If there are multiple arguments, we can specify them in a comma-separated manner or by expanding this interface. But in our case, there is just a single argument, which is the total supply of tokens which will be in circulation. Remember that this is a value which cannot be modified after a contract has been deployed. So we are now fixing the supply of our Looney tokens at 50 units. With this argument specified, all we need to do to deploy our tokens to the blockchain network is to hit the deploy button. And once we do that, we immediately get the notification both in the left menu as well as in the console that this deployment transaction has gone through successfully. So we have now created a token which complies with Ethereum's ERC20 standard. To view the details of the deployment, we can expand this message in the console, and this will give us a lot of the transaction related details. And now that our token is available on the Ethereum network, it is time for us to ensure that all of the features or all of the functions which we defined work exactly as expected, and that this can in fact be used as a tradable token. We will do that by interacting with this deployed contract in the next video. With our custom token now deployed to a virtual Ethereum network provisioned by the Remix IDE, we can begin testing out our token by interacting with the deployed contract and then testing out its various functions, and then making sure that the events which we defined are being emitted just as we wanted to. So to begin the contract interactions, we can expand this interface in the deployed contract section, and this will show to us the different operations which are permitted on our deployed contract. The ones which are shaded in orange are the ones which invoke transactions, whereas the blue buttons denote operations which will only read from the contract state. The buttons for decimals, name, and symbol are getters for the 3 fields which we defined within our contract. Now, to test these out, we can just begin invoking each of these operations one by one. Firstly, To receive the value of the decimals variable, we hit the decimals button, and this returns the value of 18, just as we had defined within our contract. The value of 18 is available just below the decimals button, and we can also see from the console that this triggered a call operation on the contract. By expanding it, the full details of the call will be available. And now we will move ahead and trigger the name getter. This will return to us the full name of our ERC20 token, which is Looney in my case. Again, we can expand the call operation from the console. And now we will go ahead and get the value of our symbol for the token. And this is again correctly defined as LNY. Now, all of these three fields were hard-coded in our contract, and we will now trigger one of the functions which we defined, which you will recall is a compulsory function to comply with the ERC20 standard. And this is to return the total supply of our token in circulation. So this is a function call which returns a value of 50. We can expand the console message to view the full result of this call operation. So this includes a transaction hash, for example, and right at the bottom in the decoded output field, we can see this value of 50, which has been returned. Now it is time for us to check the other operations here. So for example, if you wish to check the balance of tokens in a particular account, we can trigger the balance of function, whose argument is an account address whose token balance we wish to check. So to do that, I'm going to head over to this account dropdown, and the first of the accounts has been selected from here. And there is this copy button right next to it, which we can use to copy over the entire account address. With that copied over to the clipboard, I'm going to head down to this balance of button. And here we can expand this little interface where we can see the name of the argument which needs to be supplied to balance off. So this is token owner. And I'll just go ahead and paste the address of the account right here. Now remember that this particular account was the one which was used to deploy the ERC20 smart contract. And the way we had coded up the constructor of our contract, the entire initial supply of 50 tokens should be allocated to the one deploying the contract, which will be this address whose balance we're about to check. So when we hit the call button here, just as we should expect, the value of 50 tokens is returned. So this account is in possession of 50 units of the Looney token. Now let us go ahead and check the balance of this token for one of the other accounts. So heading to this accounts dropdown, I'm selecting the second one from the list. And then I will go ahead and copy over this address, head back to the balance of function, and then perform another call operation in our contract. And this returns a value of 0, which again is correct because this address has not been allocated any of our tokens. Since all of the Looney tokens were allocated to the account which was used to deploy the contract, it is up to that account to distribute the tokens so that more users are in possession of it. There are a couple of ways to distribute the token. One of these is to invoke the transfer function so that the tokens are transferred over to one of the other accounts. And the other is to delegate one of the other accounts to spend tokens on your behalf. That requires the invocation of the approve function. Now to invoke either approve or transfer, we need to be connected to the network as an account which is in possession of tokens. So we can now head over to the account section and then switch over to the first account, which at this point in time has a stranglehold on all of the tokens in circulation. Also note that the current contents of our clipboard is the address of the second account, which in my case ends in 160C. Now with the selection of this first account and the address of account number 2 in my clipboard, I'm going to head over to the transfer function and then expand this menu here. So there are two arguments which we need to supply to transfer. The first of these is the recipient, and I'm pasting in the address of the second account in my list. So just to summarize, this is a transfer from account 1 to account 2, and the number of tokens which are being transferred are 20. Given that account 1 has a current token balance of 50, this transaction should go through. So when we hit the transact button, we can see from this green check mark in the console that this transaction was successfully mined. We can expand this to view the details of this operation. So we can see, for example, that the transfer event was also emitted, and the event logs will display the source of the transfer, the destination, as well as the number of tokens which were involved. So at this point, we expect that the token balance for account 2 will be 20 and that of account 1 should be 30. To check that, we can head back to the balance of function in the menu, and the address of account 2 is already pasted here, so we'll just trigger the call operation once more. And this correctly returns the value of 20. So we now know that account 2 has received the 20 tokens which was sent to it. But what of account 1? Has its balance reduced by 20 tokens? Well, to check, we head back to the accounts menu, select account 1, and the purpose for this selection is just to copy over the account address. So with account 1's address in the clipboard, we head back to the balance of function, paste in this address, and then hit the call button. And the token balance for account 1 is now 30. So we now have two different accounts which are in possession of the Looney tokens. Account 1 has a balance of 30 tokens, and account 2 has 20 of them. And we have also successfully tested out the transfer operation defined within our contract. The other feature which we now need to test out is when we delegate another account to spend tokens on our behalf. This involves the use of the approve, allowance, and transfer from functions, which we will test out in the next video. Having successfully tested out the transfer operation for our token, it is now time for us to test out the scenario where one account allocates some of their tokens to another account to spend on their behalf. At the moment, we have account number 1, which possesses 30 tokens, and account 2, which has 20. We will test out the scenario where account 1 allocates some of its 30 tokens to account 2 to spend on its behalf. And to do that, we will need to trigger the approve function first. That function needs to be invoked by the token owner, and its argument includes the delegate who is authorized to spend tokens on their behalf. So for account 1 to authorize account 2 to spend tokens, we will need to copy over the address of account 2. So we head over to this accounts dropdown, select account number 2, and then hit the copy button. But in order to invoke the approve function as account 1, we will need to switch back to that account. And with that done, we head over to approve, expand this menu for the arguments, and then paste in the address of account number 2 and the number of tokens which account 1 authorizes account 2 to spend on its behalf is 10. We can now hit the transact button to grant this authorization, and this transaction has also gone through successfully. When we expand this message in the console, we can head over to the log section where we can confirm that the approval event was emitted. And the arguments to the approval event are right here, which includes the address of the token owner as well as the delegate, along with the number of tokens which are being allocated. Now, to ensure that this allocation has taken place successfully, we will need to trigger the allowance function. The arguments to that include the addresses of the token owner as well as the delegate. So now to copy over the address of account 1, I'm just heading back up here and then hitting the copy button and then heading back down to allowance. We will set in the token owner as account 1 and will then copy over the address of account 2 from this call to approve and paste that in as the second argument to allowance. And with that, when we invoke this call, we expect to see how many tokens account 1 has delegated to account 2 to spend on their behalf. And the answer is correctly returned as 10. And we can view the details of this call in the console. But we now know that account 2 has the authorization to spend 10 units of account 1's tokens. The test for us now is to invoke the transfer from operation where account 2 spends some of account 1's tokens. The thing to keep in mind here is that account 2 possesses some of its own tokens, so we need to ensure that the tokens which are transferred over are from the account of number 1 rather than from account 2's own balance. So to invoke the transfer from operation as the delegate, we need to be connected to the network as this delegate. So I'm now switching over from account 1 to account 2, heading over now to the transfer from function. We expand this menu and then supply the arguments. Now, the owner of the token will be account 1. So I'm now copying over that address from this call to allowance and pasting it here. So this account 1 is the owner of the token. As for the recipient of this transfer, we can go ahead and select account number 3 from this account list. So with this selection made, I'll just copy that address to the clipboard, head back down to our transfer from function call, and then paste in this address as the token buyer or the token recipient. This transfer from operation needs to be executed as the delegate. So we will perform one more account switch. So switching over to account number 2, and then heading back down to the transfer from function, we enter the last of the 3 arguments here, which is to transfer over 5 tokens. And before we hit the transact button, let us quickly summarize what exactly we are doing here. Account number 2 is transferring 5 tokens from the balance of account 1 to that of account number 3. Account 2 is currently authorized to spend 10 tokens on behalf of account 1, so this is well within those limits. And after this transaction has been processed, we expect that the token balance of account 1 will drop by 5, that of account 3 will increase by 5, and the token balance of account 2 will be unchanged. So when we hit transact, this transaction has gone through successfully. And expanding the message in the console, we can scroll down and confirm that the transfer event has been emitted and that the from and to addresses along with the number of tokens are accurate. So it is now time for us to check the token balances in each of these accounts. So we can copy over the address of the recipient here, which is account 3. But before we check account 3's balance, we can confirm the balance of account number 1. When we previously made that call, that account had a balance of 30 Looney tokens, and now we expect that this balance will be 25. And when we call this function, this does indeed return a value of 25 tokens. That value is available below the balance of button, and we can view the entire contents of the call in the console. So 5 tokens have made their way out of account 1. But did they hit account 3? For that, we head back to the balance of function, and then we paste in the address of account 3, which is already in our clipboard, and then make this function call. And the value which is returned is 5. So the token balances of both the source as well as the recipient in the transfer from operation have been correctly updated in our contract. Now, as a sanity check, we should check the token balance of account 2 and ensure that even though it performed this transfer, none of its own tokens were affected. So I'm now copying over the address of account 2 and then heading back to the balance of function. We'll paste in that address and invoke this call. And the balance of account 2 has been correctly returned as 20 tokens. So we have now successfully tested out all of the different functions within our ERC20 smart contract. This also means that we have correctly defined a token for the Ethereum network which complies with the ERC20 standard. You can now use such a token as a bespoke currency for your own Ethereum applications. But if you are using it in a production setting, there will be multiple changes which you will likely make. For example, you may not want the token supply to remain constant, but as something which can be updated periodically. But this demo does give you an idea of how such a token can be defined and implemented. In this exercise, you'll start off by listing and then describing the two events which must be implemented in a smart contract which defines an ERC20 token. ERC20 is a standard which defines a token which can be used on the Ethereum network. And during this course, we implemented such a token which requires the inclusion of certain functions and events in the smart contract defining the token. You will need to recollect what the events are and what purpose each of them serve. Next, you will summarize the details of the transfer from function for an ERC20 token. So among the different functions which need to be implemented in order for your token to comply with the ERC20 standard, transfer from serves a special purpose, and you will need to recall what exactly that is and some of the other related operations which your token definition must also include. Each of these topics were covered during this course, so please pause this video and then take some time to do this exercise on your own. For the first task in the exercise, you needed to list the two events which need to be implemented in your token definition in order to comply with the ERC20 standard. The first of these events is called transfer. So this is emitted each time a call is made to either the transfer function or the transfer from function, both of which involve the transfer of tokens from one Ethereum account address to another. So this transfer event does record the transfer of tokens. Now the details which need to be included when this event is emitted are the address of the account from which the transfer is taking place and also the address of the recipient of the token. In addition to that, the number of tokens being transferred from the originator to the recipient will also be included in the event details. So this covers the transfer event. The second event which the token needs to include is one called approval. We saw during the token implementation in the course that you can authorize some other Ethereum account to spend your own tokens on your behalf as long as you grant them the approval to perform such an operation. To do that, you will call the approve function, and this approval event is emitted when you invoke that function. So when you call approve, you're authorizing a delegate to spend tokens on your behalf. So the event details for this need to include the address of the token owner along with the address of the authorized delegate. Also, the number of tokens which the delegate is authorized to spend on behalf of the owner will be included in this information. In addition to these two events, there are also 6 functions which need to be implemented in order for your token to comply with the ERC20 standard. And it is one of those 6 functions which you needed to describe for the next task in the exercise. So this is the transfer from function. And we covered the fact that the approve function is invoked by the owner of tokens in order to allow a delegate to spend tokens on their behalf. Now, once the delegate has the authority to spend those tokens, it is the transfer from function which they will need to invoke. So here we have the signature of the transfer from function, which includes 3 arguments: the address of the token owner, the address of the recipient of the tokens, and also the number of tokens which are being transferred from the account of the owner to the recipient. This function returns a Boolean value, and this will be true if the transfer operation was a success. As touched upon, this is a function which is invoked by a delegate on behalf of the token owner, and this will transfer n tokens from the owner's account to that of the recipient. And while you're implementing this transfer from function, you should perform a check to ensure that the owner which is specified in this transfer from function does indeed possess at least the number of tokens which are being transferred. Another check which you should be implementing is to ensure that the delegate who is invoking this function does have the prior authorization which is required from the owner in order to spend their tokens. If this authorization is not available, then the owner will need to use the approve function to grant the permissions to the delegate. So one important thing to keep in mind with the transfer from operation is that this involves a transfer of tokens from an owner to a recipient, and this is a function which is called by a delegate. The delegate's own tokens are completely unaffected by this operation.